Hello there, and welcome to Science for Sleep, where complicated ideas are given enough room to slow down, settle into place, and become a little less intimidating before bedtime. Tonight we're going to explore wormholes, those strange theoretical passages that appear in the mathematics of gravity and have spent decades causing trouble for physicists, filmmakers, science fiction writers, and anyone who has ever looked at a long journey and wished the universe came with a shortcut. Before we begin, where are you listening from tonight? Are you somewhere quiet with the room already dark, or are you still moving through the last part of your day? And if a wormhole could carry you safely to any place in the universe, with no unpleasant stretching, no mysterious radiation, and no missing luggage, where would you choose to go? You might visit a distant planet, the center of the Milky Way, or a place so far away that its light has not had enough time to reach Earth. You might choose somewhere more familiar, perhaps the other side of the world, a childhood home, or simply the kitchen, because getting out of bed now feels unnecessarily ambitious. Wormholes are usually discussed on a cosmic scale, but the basic appeal is very ordinary. We do not enjoy taking the long way when a shorter route might exist. If you find these slow scientific journeys relaxing, you can leave a like and subscribe to the channel. It helps more listeners find this quiet corner of science, and it tells the machinery behind the screen that calm explanations of theoretical physics are apparently something people would like more of. That is useful information for the machinery, which otherwise has to make rather a lot of guesses. Settle into a comfortable position, let your breathing find its own pace, and allow the day to become less important for a while. There is no need to remember every name, equation, or distinction. Wormhole physics can become extremely technical, and even professional physicists disagree about what kinds of wormholes might be possible, what might keep them open, and whether nature permits them outside mathematics. Tonight, we can take the subject one step at a time. The simplest description of a wormhole is a connection between two regions of spacetime. That wording matters. A wormhole is not merely a tunnel through ordinary space, like a railway tunnel cut through a mountain. In Einstein's theory of general relativity, space and time are joined into a four-dimensional structure called spacetime. Matter and energy affect its geometry, and that geometry affects how matter, light, clocks, and planets move. Gravity in this description is not an invisible rope pulling objects together. It is the result of objects following paths through curved spacetime. This is already a strange idea, although daily life hides the strangeness rather well. The floor feels solid, the walls remain where they were placed, and a cup left on a table does not usually reveal the geometry of the universe. Yet every object around you is moving through spacetime. Earth travels around the sun moves through the Milky Way, and the Milky Way moves relative to other galaxies. At the same time, every clock is advancing, every atom is changing, and every listener is moving from one moment to the next without being asked whether the timing is convenient. A wormhole would alter the available routes through that structure. Imagine two locations that are very far apart when measured along the normal path through space. A beam of light may need years, centuries, or billions of years to travel between them. If spacetime had a suitable connection, there could be another route whose internal distance was much shorter. Enter one side, move through the connecting region, and leave through the other side without crossing all the ordinary space in between. The usual illustration involves a sheet of paper. Mark two dots far apart, fold the paper until the dots touch, and push a pencil through both points. The whole represents a shortcut. It is a helpful picture, but it can also be misleading. The paper suggests that space-time must bend into a larger surrounding room, as though the universe were a sheet placed inside some higher dimensional office. Some mathematical descriptions use extra dimensions, but a wormhole in general relativity does not always require us to imagine a literal external space. The important point is the internal geometry. Two regions can be connected in a way that creates a route not available in ordinary flat space. Physicists often describe a wormhole as having two mouths and a throat. The mouths are the entrances, although the word entrance makes the arrangement sound more welcoming than it may be. The throat is the connecting region between them. Depending on the solution, the mouths could lie in distant parts of the same universe, in different times in different universes, or in mathematical regions that cannot be reached by a traveller at all. Some wormholes exist only for an instant. Some collapse before light can cross them. Some require unusual forms of energy to remain open. Some appear in quantum theories where the word tunnel becomes more of a mathematical description than a place where anyone could park a spacecraft. This is why there is no single wormhole type. The name covers a large family of theoretical structures. They can be classified by geometry, by the matter or energy associated with them, by whether they rotate or carry electric charge, by whether they can be crossed, by whether they connect two locations or two times, and by whether they belong to classical gravity or quantum models. Two objects may both be called wormholes while behaving so differently that placing them in the same category feels a little like grouping a footpath and an airport, because both can help you leave town. The first major distinction is between traversable and non-traversable wormholes. A traversable wormhole allows matter or signals to pass from one side to the other and emerge somewhere else. The traveller must be able to enter, survive the journey, and leave. This sounds obvious, but mathematical wormholes do not owe travellers any practical consideration. A solution can contain a bridge without allowing anything to cross it. The throat may close too quickly. An event horizon may block the route. A singularity may end the journey. Tidal forces may turn a spacecraft into a very long and very unsuccessful spacecraft. Non-traversable wormholes are still important because they reveal what Einstein's equations permit. They may connect regions of a mathematical spacetime even when no observer can use the connection as a passage. The best-known early example is associated with Albert Einstein and Nathan Rosen, who described a bridge between two sheets of space in 1935. Their purpose was not to design an interstellar transport system. They were studying a problem involving particles, fields, and singularities in general relativity. The modern image of an Einstein-Rosen bridge as a convenient portal came later, after the original mathematics had entered a much broader scientific and cultural story. That bridge is often linked with black holes. A black hole forms when gravity becomes strong enough to create a region from which light cannot escape. In certain idealized solutions, the complete mathematical spacetime contains more than the exterior region normally shown in simple diagrams. When those solutions are extended, another exterior region can appear, connected through a bridge. But the connection is not a stable corridor. It closes too quickly for a signal or traveller to pass through from one exterior region to the other. You can draw the bridge, you can describe it, you cannot book a seat through it. Traversable wormholes were studied in a more practical form during the late 20th century. Researchers asked what geometry would be required for a throat to remain open, avoid an event horizon, and allow a traveller to pass without encountering destructive forces. The resulting models showed that general relativity could describe such a route, but usually at a cost. The throat would need matter or energy with unusual properties, commonly described as exotic matter. In many models, this material violates standard energy conditions, which are assumptions about how physically reasonable matter should behave. The phrase exotic matter tends to encourage dramatic images. It does not necessarily mean a glowing substance stored in a forbidden container beneath a laboratory. It refers to stress and energy arranged in a way ordinary matter does not normally provide. In a simple traversable wormhole model, gravity would tend to make the throat collapse. Something would have to oppose that collapse and hold the passage open. The mathematics often requires negative energy density, at least from the viewpoint of certain observers, or another effect that produces the required geometry. Quantum physics does allow limited situations that can be described using negative energy, relative to a chosen vacuum state. The Casimir effect is often mentioned in this context, because quantum fields between closely spaced conducting plates can produce an energy difference that behaves as negative relative to the surrounding vacuum. but a small quantum effect between plates is not the same as a stable, human-sized wormhole. Moving from one to the other is not a minor engineering upgrade. It is more like noticing that a soap bubble can resist pressure and concluding that the same method should hold open a tunnel through a star. There are also wormhole solutions involving electric charge. In an idealized charged black hole spacetime, the geometry can contain multiple horizons and connections to other regions. Rotation creates another set of possibilities. A rotating black hole is described by the Kerr solution, and its extended mathematical structure includes paths that do not appear in the simpler non-rotating case. These diagrams can contain other universes, white hole regions, and routes around a ring-shaped singularity. They are fascinating, but they also come with warnings. Idealized solutions may be unstable. Small disturbances, radiation, or realistic matter can change the interior dramatically. Mathematics may provide a doorway that nature immediately fills with debris and locks from the other side. Thin shell wormholes take a different approach. Instead of relying on a naturally occurring bridge, theorists can construct a wormhole mathematically by cutting regions from known spacetimes and joining the remaining boundaries. The joining surface becomes a thin shell, and the equations determine what kind of matter or stress must live there. It is a little like taking two pieces of a model universe, trimming them carefully and sewing the edges together. The sewing is exact. The fabric is space-time. The required thread is usually something no shop currently sells. At much smaller scales, quantum theories introduce wormholes that may not resemble large tunnels at all. Some approaches to quantum gravity suggest that space-time could fluctuate at extremely short distances. Instead of remaining smooth, it might develop temporary changes in topology, including tiny connections sometimes discussed as part of quantum foam. These structures would be unimaginably small and brief. They would not be miniature subway systems waiting for a sufficiently small passenger. They are attempts to describe how geometry might behave when quantum uncertainty applies to space-time itself. Euclidean wormholes belong to another mathematical setting. In many quantum gravity calculations, physicists replace ordinary time with a mathematical coordinate sometimes called imaginary or Euclidean time. This can turn a difficult space-time problem into a geometric one that is easier to handle in a path integral. Wormholes in this framework can connect separated regions of Euclidean geometry and influence calculations involving quantum states, fields, or the possible values of physical constants. They are not necessarily tunnels through which an observer travels. They function inside the mathematics used to calculate probabilities. More recent ideas connect wormholes with quantum entanglement. Entanglement occurs when quantum systems share correlations that cannot be described by assigning each system a completely independent state. A proposal often written as ER equals EPR suggests a deep relation between Einstein-Rosen bridges and entanglement. The idea does not say that every pair of entangled particles contains a tiny usable tunnel, nor does it allow a message to be sent faster than light. Instead, it suggests that certain geometric connections in a theory with gravity may be another way of describing patterns of quantum entanglement. This possibility has attracted attention because modern physics has two extraordinarily successful theories that remain difficult to combine. General relativity describes gravity, planets, stars, black holes, and the large-scale structure of the universe. Quantum mechanics describes particles and fields at small scales. Both work extremely well in their proper domains. When physicists try to apply them together in extreme situations, especially inside black holes or near the beginning of the universe, the mathematics becomes difficult and incomplete. Wormholes sit directly in this uncomfortable meeting place. They force questions about geometry, information, energy, causality, and the quantum structure of space-time. Causality is the rule that causes come before their effects. It is so basic to experience that we rarely need to state it. You drop a spoon, and then it hits the floor. The floor does not make a sound 5 seconds earlier in order to remind you that a spoon will soon be dropped. Wormholes can complicate this order because the two mouths may experience different amounts of time. If one mouth moves at high speed, or remains in a stronger gravitational field, relativity says its clock can advance at a different rate from the clock at the other mouth, bring the mouths back into a useful arrangement, and passing through the wormhole might connect not only different places but different times. That possibility turns a shortcut into a time machine. It also creates paradoxes. A traveller might return before departure. A message might prevent itself from being sent. An event could become its own cause. Physicists have proposed several ways nature might avoid such contradictions. Perhaps traversable wormholes cannot exist. Perhaps quantum effects destroy a time machine as soon as it becomes possible. Perhaps events remain self-consistent, allowing travel but not allowing history to be changed. Perhaps timelines branch. At present, these options belong to theory, not observation. That last point is worth keeping close throughout our journey. No wormhole has been directly observed. Astronomers have detected black holes, measured gravitational waves from their collisions, tracked stars moving around invisible massive objects, and photographed the glowing material near black hole shadows. Wormholes remain hypothetical. A strange object in space might imitate some features of a black hole, and researchers have considered whether lensing, radiation, orbital motion, or gravitational waves could reveal a wormhole. So far, there is no accepted evidence that any astronomical object is one. The absence of evidence does not make the subject pointless. Theoretical physics often studies what equations allow before nature provides an example. Black holes were mathematical solutions long before there was strong observational evidence for them. Gravitational waves were predicted a century before detectors measured them directly. This does not mean every mathematical object will eventually be found. It means that exploring a theory's unusual solutions can reveal where the theory is strong, where it becomes uncertain, and what observations might distinguish one possibility from another. Wormholes are particularly useful because they test the limits of several ideas at once. Can spacetime change its topology? Can negative energy exist in a large and stable arrangement? Does quantum theory protect causality? What happens to information when geometry connects distant regions? Are space and time fundamental, or could they emerge from deeper quantum relationships? A wormhole may sound like a transport problem, but the deeper questions concern what the universe is allowed to be. Popular culture usually simplifies the journey. A circular gate opens, a ship enters, there is a brief display of lights. Everyone arrives near the correct planet, often with enough time remaining for an emotional conversation. Real theoretical models are less cooperative. The entrance may be microscopic. The throat may collapse. Radiation may build up. The destination may be unreachable. The passage may require impossible control over matter and energy. Even deciding whether the traveller survives can require careful calculations of acceleration, tidal gravity, and the geometry along the route. Suppose, however, that a stable traversable wormhole existed. The mouths would not necessarily look like dark holes cut into the air. Light from the far side could pass through, so an observer might see a distorted image of the destination. The appearance would depend on how light rays bend near the mouth. There could be multiple images, rings, bright regions, and unusual magnification. Looking into a wormhole might be less like staring into a tunnel, and more like looking through an extremely complicated lens whose frame is made from gravity. Crossing the mouth would also be different from accelerating through all the intervening space. Locally, the traveller might move at an ordinary speed and never exceed the speed of light. The shorter journey would come from the geometry. This distinction allows wormholes to create an apparent shortcut without requiring a spacecraft to race through nearby space faster than light. Relativity limits motion through spacetime, but a curved or connected spacetime can change the distance that needs to be crossed. Of course, saying that the geometry does the work is not the same as explaining how to build it. General relativity tells us how matter and energy relate to curvature. To create a particular curvature, one must provide the corresponding distribution of matter, pressure, tension, and energy. A wormhole throat is not held open by optimism. The equations require support, and the required support is where many proposals become speculative. Different theories modify the rules. In some alternatives to general relativity, higher curvature effects, extra fields, or additional dimensions can reduce or change the need for exotic matter. Cosmological settings may allow wormhole-like solutions not found in simple flat backgrounds. Brainworld models can place ordinary matter on a lower dimensional surface, while gravity explores a larger space. Each framework produces its own collection of tunnels, bridges, throats, and restrictions. The word wormhole remains the same while the underlying physics changes considerably. This is why a tour of wormhole types must begin carefully. We are not cataloguing confirmed objects in the way we might catalogue planets, stars, or species of bird. We are organising possibilities found in different equations and theoretical frameworks. Some are classic solutions of general relativity. Some are designed geometries that require special matter. Some appear only after extending a mathematical spacetime beyond the region an ordinary observer could reach. Others belong to quantum gravity, holography, or Euclidean calculations. Their names sometimes overlap, and the same term can be used differently by different authors. During this journey, we will keep asking a few practical questions. What does each wormhole connect? Can anything cross it? What keeps it open? Does it contain a horizon or singularity? Does it require negative energy? Could it link different times? Is it expected to exist in nature, or is it mainly a mathematical tool? Those questions prevent the subject from becoming a collection of impressive names, with no clear differences between them. We should also avoid treating possible in an equation as possible to construct. An equation may permit a solution under exact assumptions that the universe never provides. A perfectly rotating black hole, an eternal space-time with no disturbances, or a shell of precisely arranged exotic matter can be useful for understanding the theory. It does not follow that an engineer can gather the required materials on Tuesday and begin construction after lunch. Still, the fact that wormholes continue to appear is interesting. They emerge in studies of black holes, quantum information, cosmology, gravitational instantons, alternative gravity, and the foundations of space-time. They may be impossible as transport systems and still be valuable as theoretical laboratories. By pushing a theory toward its strangest allowed configurations, physicists can learn what assumptions are doing the real work. Keep the familiar image of a cosmic shortcut, but hold it lightly. Some wormholes are bridges that no one can cross. Some are supported tunnels that may demand exotic energy. Some rotate, some carry charge, some exist in imaginary time, some connect mathematical universes. Some may describe quantum entanglement in geometric language. Others may turn a route through space into a route through time, which is where even a quiet bedtime discussion can begin causing logical difficulties. Our first stop lies with the structure that gave wormholes their most famous scientific name. In 1935, Albert Einstein and Nathan Rosen were not trying to design a route to another galaxy. They were not planning a doorway through space, and they were certainly not wondering whether a traveller could step into one black hole and emerge beside a distant star. Their problem was smaller, more technical, and in its own way more ambitious. They wanted to know whether general relativity could describe particles without placing an infinite breakdown in the middle of the mathematics. General relativity had already changed the meaning of gravity. Instead of treating gravity as a force acting across empty space, it described matter and energy as curving space-time. Objects then moved along the available paths through that curved geometry. The theory explained the orbit of Mercury more accurately than Newtonian gravity, predicted the bending of light near the Sun, and allowed physicists to study stars, planets, and the universe as geometric systems. It was an extraordinary success. It also produced singularities, places where quantities in the equations could become infinite and the description stopped being reliable. Einstein disliked singularities. An infinity in an equation can sometimes indicate a real physical extreme, but it can also mean that the theory has been pushed beyond the region where it makes sense. When a model says density, curvature, or another quantity becomes infinite, a physicist has to ask whether nature truly contains an infinity, or whether the model is missing something. Einstein and Rosen hoped to avoid the problem by representing a particle not as a point with a singular field, but as a smooth geometric structure. Their paper was called The Particle Problem in the General Theory of Relativity. The title is useful because it reminds us what they believed they were studying. The bridge was intended as a model of a particle. It was not introduced as an interstellar passage. In the simplest case, the geometry contained two identical sheets of space joined at a surface. Einstein and Rosen referred to the connection as a bridge. A particle, in their proposal, could be represented by that bridge rather than by a singular point. To picture the two sheets, imagine two copies of the same exterior region around a spherical object. Each copy contains distances extending outward, away from a central boundary. At that boundary, the two copies are joined. This is often represented as two curved funnels attached at their narrow ends. Each funnel widens away from the join, while the narrow connection between them forms the bridge. The familiar rubber sheet picture must be handled carefully. It shows curved space by placing a surface inside an ordinary three-dimensional room. But the room is only a visual aid. The actual geometry does not require a literal workshop outside the universe, where someone has folded space-time and applied glue. What matters is how distances are measured within the geometry, and how paths continue from one region into another. Einstein and Rosen began with the Schwarzschild solution, which describes the space-time outside an idealized, spherical, non-rotating, uncharged mass. Carl Schwarzschild found this solution in 1916, only a short time after Einstein completed general relativity. The Schwarzschild geometry contains a special distance now called the Schwarzschild radius. For an object compressed inside that radius, the modern interpretation is a black hole surrounded by an event horizon. The language of black holes was not yet standard in 1935. Even the term black hole would not become widely used until decades later. Einstein and Rosen were looking at a mathematical difficulty in the Schwarzschild coordinates. At the Schwarzschild radius, certain terms appear to become infinite or vanish in a suspicious way. Today, physicists know that this behavior is largely a coordinate problem. A coordinate problem is easier to understand with an example from Earth. Lines of longitude work well across most of the planet, but they all meet at the poles. At the North Pole, asking for a unique longitude becomes awkward. Nothing physically terrible happens to a traveller standing there. The difficulty belongs to the system used to label locations, not to the surface of Earth itself. Something similar happens at the Schwarzschild radius. The original coordinates become poorly behaved, but the event horizon is not necessarily a place where the curvature of space-time becomes infinite. A different coordinate system can describe an observer crossing the horizon without the equations breaking down there. This is known as a coordinate singularity. It can be removed by choosing a better way to label events. A genuine curvature singularity cannot be removed so easily. In the classical Schwarzschild spacetime, the central region at zero radius contains a true breakdown where curvature becomes unbounded, and ordinary general relativity can no longer provide a complete description. Einstein and Rosen introduced a new radial coordinate that avoided treating the troublesome region as a single singular point. Their transformation produced a geometry with two copies of the exterior space joined at a shared boundary. Instead of ending at the centre, the spatial description continued into a second sheet. The resulting object was static in the form they presented. From the viewpoint of the spatial geometry, there was a minimum spherical surface where the two sheets met. Moving inward on one sheet brought you toward that minimum sphere. Continuing through the mathematical construction led outward along the second sheet. It looked like a smooth connection rather than a path ending at a point of infinite curvature. This was the original Einstein-Rosen bridge. The name now appears in discussions of wormholes, black holes, quantum entanglement and science fiction. But the original goal was to create a non-singular model of matter using geometry. Einstein and Rosen hoped that many particles might eventually be represented by many bridges connecting the two sheets. They had not solved that many-particle problem, and they stated this clearly. Their bridge was an early proposal rather than a completed theory of matter. It showed how a geometric connection might replace a singular particle in one simplified situation, but it did not explain the full collection of particles found in nature. There was also an electrically charged version. Einstein and Rosen considered gravity together with electromagnetism and looked for a regular description that could represent a charged particle. This reflected a broader hope Einstein pursued for many years. Perhaps matter could be explained entirely through fields and geometry. Instead of placing particles into space-time as separate ingredients, particle-like objects might emerge from the structure of the fields themselves. That program did not become the accepted description of elementary particles. Modern particle physics uses quantum field theory, and the particles of the standard model are not treated as large bridges between two copies of space. Even so, the 1935 construction introduced an idea that remained valuable. Geometry could connect regions in a way that resembled a passage, and the complete mathematical structure of a gravitational solution might contain more than one exterior region. The next important step came from learning how to describe Schwarzschild spacetime more completely. The original Schwarzschild coordinates hide part of the geometry because they become badly behaved at the event horizon. Later coordinate systems showed that an observer falling through the horizon would not encounter an infinite wall at that location. For a sufficiently large black hole, crossing the horizon could be locally uneventful. There might be no surface to strike, no flashing boundary, and no helpful sign announcing that returning home had just become impossible. The observer would still face serious trouble farther inside, but the event horizon itself would not necessarily produce an immediate physical shock. A distant observer and a falling observer would describe the crossing differently. From far away, the falling object appears to slow as it approaches the horizon. Its light becomes increasingly redshifted, weaker and more delayed. The distant observer does not receive a final signal saying, "I have now crossed," because signals emitted closer to the horizon take longer to arrive and lose more energy. From the falling observer's own viewpoint, the situation is different. Their clock continues to tick, and they can cross the horizon after a finite amount of personal time. They do not wait forever at the boundary. The apparent freezing belongs to the distant coordinate description and to the changing light signals, not to the traveller's own local experience. In 1960, Martin Kruskal published a coordinate transformation that displayed the maximal extension of Schwarzschild spacetime clearly. Similar work was developed independently by George Zekaris. The new coordinates removed the artificial breakdown at the event horizon and revealed the full causal structure of the idealized solution. The extended diagram contains 4 main regions. One represents an exterior universe like the region outside an ordinary black hole. A second represents another exterior region. A third corresponds to a black hole interior, and a fourth corresponds to a white hole interior. A white hole is the time-reversed form of a black hole. Matter and light can cross into a black hole but cannot return once they pass the horizon. In the idealized white hole region, matter and light can emerge, but nothing from the exterior can enter it. No confirmed white hole has ever been observed. The white hole region appears because the eternal Schwarzschild solution is extended as far as its mathematics allows, both into the future and into the past. It is part of the complete idealized geometry, although that does not mean nature produces such objects. The 2 exterior regions in the Kruskal diagram are connected geometrically. The narrow connection between them is commonly called an Einstein-Rosen bridge. This is the version most people mean when they say that a Schwarzschild black hole contains a wormhole. The word contains can create the wrong impression. It sounds as though a stable tunnel waits behind every event horizon, perhaps requiring only a brave crew, a powerful engine, and a regrettably expensive insurance policy. The complete eternal solution is much less accommodating. The bridge does not behave like a corridor that remains open for travellers. Its shape changes with time. At one stage in the idealized geometry, a spatial slice can show a throat connecting the two exterior regions. The throat grows to a maximum size and then closes. No light ray or slower object can move from one exterior region to the other before the connection pinches off. This is why the standard Einstein-Rosen bridge is described as non-traversable. The geometry has a connection, but no traveller can use it to complete a journey from one exterior side to the other. Suppose two observers live in the two separate exterior regions. Each observer might see what appears to be a black hole from their own side. A carefully chosen spatial surface passing through the full geometry could show a bridge between them, yet neither observer could send a message through the black hole to the other. Any signal that crosses the future event horizon moves into the black hole interior. It does not emerge in the opposite exterior region. The future paths available to the signal lead toward the singularity. This becomes easier to understand when we separate a spatial picture from a journey through space-time. A diagram of space at one selected moment can show a connected shape. A traveller, however, follows a path through the full four-dimensional space-time. The question is not merely whether two places are joined on a map. The question is whether a future-directed path can carry matter or light from one place to the other. In the Einstein-Rosen bridge, the allowed paths do not complete that crossing. The bridge closes too quickly. A picture may show the two sides touching, but the full history of the geometry prevents anyone from moving through the connection before it disappears. A photograph of an open lift door would not guarantee that the door remains open long enough to enter, especially if the lift also leads directly into a gravitational singularity. The photograph is not false, it simply does not include enough information about what happens next. The word tunnel therefore needs a warning label. An Einstein-Rosen bridge is a geometric connection in an extended space-time, but it is not a safe tube with two permanently open ends. Entering from one side does not produce an exit from the other. The traveller reaches the black hole interior and, in the classical description, eventually encounters the singularity. This is one of those occasions when the universe permits an attractive diagram and refuses the practical application. There is another important complication. The maximally extended Schwarzschild solution describes an eternal black hole. It has existed for all past time within that idealized model and continues into the future. Its full structure includes a white hole region and two asymptotically separate exteriors. Real astrophysical black holes are believed to form through physical processes. A massive star can exhaust the fuel supporting its core. If the remaining mass is large enough, pressure may no longer resist gravity, and the core collapses. Black holes can also grow by absorbing matter or merging with other black holes. The spacetime produced by collapse does not have exactly the same global structure as the eternal Schwarzschild solution. A black hole formed from a collapsing star has an exterior region connected to the surrounding universe, but it does not automatically produce a second exterior universe waiting beyond a bridge. The elegant two-sided Kruskal diagram remains extremely useful. It helps physicists understand horizons, singularities, causal relationships, and the mathematical completeness of the Schwarzschild solution. It should not be mistaken for a literal map of every black hole detected by astronomers. There is also the matter of rotation. Real stars rotate, and black holes formed from them are expected to rotate as well. The Schwarzschild solution deliberately removes rotation and electric charge to create the simplest possible case. It is a clean theoretical laboratory, not a perfect description of every object in the sky. Even within that simplified laboratory, the bridge teaches several important lessons. One is that a coordinate system can hide or distort parts of a space-time. Another is that connected spatial geometry does not guarantee a traversable route. A third is that a complete mathematical extension can contain regions that may not appear in a realistic formation process. The difference between an event horizon and a singularity is equally important. An event horizon is a causal boundary. Once an object crosses it inward, the object cannot send a signal back to the exterior. The horizon is defined by which future paths remain available. A singularity is not simply a hard object sitting at the centre. In general relativity, it is more accurately associated with paths through space-time ending after a finite amount of proper time, indicating that the space-time is incomplete. The classical equations can no longer continue the description normally. Inside the event horizon, moving towards smaller radius becomes unavoidable. Outside a black hole, you can choose to move inward or outward. You can fire engines, change course, or remain at a fixed distance if your equipment is powerful enough. Inside the horizon, every future-directed route leads farther inward. This is sometimes compared with the ordinary movement of time. You can move north or south through space, but you cannot choose to travel toward yesterday by turning around. Inside the Schwarzschild horizon, decreasing radius becomes similarly tied to the future direction. Reaching the singularity is not merely a matter of being pulled downward, it is built into the causal structure. A powerful engine cannot restore the missing route. The spacecraft may accelerate, but acceleration still has to remain within the future light cone. Every permitted future light cone inside the horizon points toward the singularity. Turning around does not create a path back outside. The second exterior region is also unreachable from the first. A route connecting them would require matter or light to move in a way the geometry does not allow. In simple terms, the traveller would have to outrun the closing bridge, and even light cannot do that. This is a subtle point because the bridge can be present on a spatial slice. The connection is real as part of that slice, but traversability depends on the entire space-time, including how the geometry changes and which direction signals are allowed to follow. Different observers may divide space-time into spatial slices differently. Relativity does not provide one universal present moment shared across the entire universe. One method of slicing the geometry may show a longer throat, while another may show a shorter one. Both can describe the same four-dimensional space-time. The apparent shape of the bridge therefore depends partly on how the snapshot is chosen. This does not make it an illusion. It means that a three-dimensional picture cannot capture the whole object. Wormholes are structures in space-time, not merely unusual shapes in space. Later researchers who wanted a traversable wormhole had to change the geometry. A usable throat could not have the same event horizon obstruction. It would need to remain open long enough for a future-directed path to enter one mouth, cross the connecting region, and leave through the other. The traveller would also need to survive. A wormhole that permits passage mathematically but tears every object apart with tidal gravity would have limited appeal. A practical model must control acceleration, curvature, radiation, and the time required to cross. These requirements may sound like basic customer service, but satisfying them changes the physics completely. Preventing the throat from collapsing usually requires unusual pressure or energy. The standard Einstein-Rosen bridge supplies no such support. The bridge later became important in discussions of black hole thermodynamics and quantum information. A two-sided black hole can be used as a model containing two exterior regions associated with two quantum systems. In some modern theories, entanglement between those systems is related to the geometric connection. The proposal called ER equals EPR takes its name from two famous sets of initials. E refers to Einstein and Rosen. EPR refers to Einstein, Boris Podolsky and Rosen, who published a separate paper on quantum mechanics in May 1935. The two papers addressed different problems. The Einstein-Podolsky-Rosen paper questioned whether quantum mechanics provided a complete description of physical reality. The Einstein-Rosen paper explored whether particles could be represented by non-singular bridges in general relativity. Modern theorists later suggested that quantum entanglement and non-traversable geometric bridges might be closely related. This does not mean that every pair of entangled particles contains a tiny tunnel suitable for transporting matter. It also does not allow someone to send a message faster than light. Quantum entanglement produces correlations between measurements performed on separated systems. It does not provide an ordinary controllable communication channel. In the same way, the geometric bridge in the standard two-sided black hole model is non-traversable. The connection may help explain the structure of quantum spacetime without acting as a secret telephone line. There are also debates about how closely the modern textbook Einstein-Rosen bridge matches the exact construction presented in the original 1935 paper. Einstein and Rosen used a particular coordinate transformation and were trying to represent particles without singularities. The maximally extended Schwarzschild geometry was developed more clearly through later work and became the standard modern image associated with their names. For our purposes, the most important point is that both versions are historical and mathematical ancestors of the wormhole idea. Neither provides the stable, two-way passage normally shown in fiction. Could such a bridge form naturally? The collapse of an ordinary star does not create the complete, eternal, two-sided Schwarzschild geometry. Speculative quantum processes might produce unusual connections, and theories beyond classical general relativity may change the answer. But no observation has shown that an astrophysical black hole is joined to another exterior region by a usable bridge. Astronomers detect black holes through their effects. They track stars orbiting invisible massive objects. They observe hot gas heated as it falls inward. They measure gravitational waves produced when black holes collide. They image the bright material surrounding dark central shadows. None of these observations has revealed an exit elsewhere. No signal has entered one black hole and been detected emerging from another. No telescope has looked into a black hole horizon and seen a distant region framed on the other side. Even in the ideal two-sided solution, an exterior observer cannot simply look through the bridge. Light from the second exterior cannot travel through the non-traversable throat and reach the first. Each observer sees the horizon belonging to their own exterior region. The mouths do not operate as windows. There is no clear circular view of another galaxy waiting on the surface. That familiar image belongs to traversable wormhole models, where light can cross the throat in both directions. The Einstein-Rosen bridge remains useful precisely because it fails in such an instructive way. It proves that general relativity can contain non-trivial connections between regions of space-time. It also proves that a geometric connection is not enough. A usable route needs the correct causal structure. For a simpler comparison, imagine a railway map showing two stations joined by a line. The map suggests a direct connection. The full timetable then reveals that the track exists for only a fraction of a second. Both entrances are behind one-way gates, and every train that enters is directed toward a terminal wall. The map was not false, it simply omitted the information needed for an actual journey. Einstein and Rosen began by asking whether geometry could replace a singular particle. Later physicists learned to interpret the bridge as part of the complete structure of an eternal black hole solution. Popular culture then promoted it into a cosmic shortcut. Each stage retained something from the one before it, but each stage changed the meaning. The original bridge gave wormhole physics its central image, two broad regions joined by a narrow throat. The Schwarzschild solution supplied the simplest gravitational setting. Kruskal's extension revealed the full causal structure. Together, these ideas produced the standard non-traversable wormhole, a connection that exists in the geometry but closes before anything can cross. That failure is not a small technical flaw. It determines the entire behavior of the object. The closing of the bridge becomes easier to understand when we stop treating a wormhole as a tunnel, sitting still in space, and start treating it as a complete history in space-time. A photograph can show a narrow passage between two sides, but a traveller does not move through a photograph. The traveller moves through a geometry that changes from one moment to the next, and in the Schwarzschild solution, that change happens too quickly for a crossing to be completed. The Schwarzschild wormhole comes from the simplest black hole solution in general relativity. It assumes a perfectly spherical object with no rotation and no electric charge. Those assumptions remove many complications and leave a spacetime described by one main property, mass. Real black holes are expected to rotate, and surrounding matter can make their environments messy, but the Schwarzschild case remains the cleanest place to see how horizons, singularities, and non-traversable bridges fit together. Outside the horizon, the geometry is static. This does not mean that objects around the black hole are motionless. Gas can orbit, light can bend, and a spacecraft can fall inward. It means that the mathematical form of the exterior gravitational field does not change with time. If the mass remains fixed, the same pattern of curvature is present tomorrow as it is today. The boundary sits at the Schwarzschild radius, given by 2 times the gravitational constant times the mass, divided by the speed of light squared. For the Sun's mass, that radius is about 3 kilometers. The Sun is much larger than this, so it is not a black hole. If the same mass could somehow be compressed inside a sphere only a few kilometers across, an event horizon would form. An event horizon is not a material shell. It has no steel surface, no layer of rock, and no membrane that a falling observer would physically strike. It is a boundary defined by causal structure. Outside it, some future-directed paths lead away from the black hole. At the horizon, the outward path of light remains on the boundary. Inside it, every future-directed path leads farther inward. This is why the usual phrase, escape velocity greater than the speed of light, is only an approximate explanation. It suggests that a sufficiently fast engine might almost succeed, or that light tries to climb outward and loses a contest against gravity. General relativity gives a more complete description. Inside the horizon, there is no outward route leading to the exterior future. The problem is not merely insufficient speed. The geometry no longer offers the destination. The Schwarzschild coordinates used in the original solution make the horizon look troublesome. A distant clock appears to slow as it approaches the Schwarzschild radius, and the coordinate time required to reach the horizon becomes infinite. This once encouraged the idea that matter might remain frozen at the boundary forever. A falling observer does not experience that result. Their own clock measures a finite interval before crossing. For a very large black hole, the horizon could be crossed without a sudden local event. The observer would not encounter an infinite gravitational force at that exact surface. The serious danger comes from tidal effects, which depend on the black hole's mass and the traveller's distance from the centre. Near a small black hole, tidal forces can become destructive before the horizon is reached. Gravity pulls more strongly on the side of an object closer to the centre than on the side farther away. A person falling feet first would be stretched along the direction of travel and compressed sideways. The cheerful technical nickname is spaghettification, a term that manages to sound less alarming than the process deserves. For a supermassive black hole, the gradient in gravity at the horizon can be much weaker. A traveller might cross first and encounter fatal tidal forces later. This does not improve the long-term travel prospects. It simply allows more time to notice that the route remains one way. To display the complete Schwarzschild geometry, physicists use coordinate systems that remain regular at the horizon. The Kruskal-Seka's coordinates are especially important because they show all regions of the maximally extended solution in a single causal diagram. The apparent singularity at the Schwarzschild radius disappears, while the genuine singularities remain. Kruskal's transformation was developed specifically to remove the artificial coordinate singularity and exhibit the full extension of the metric. The full diagram contains 2 exterior regions. Each exterior is asymptotically flat, meaning that far from the central mass, the geometry approaches ordinary flat spacetime. An observer living far away in either exterior could describe their surroundings as a universe extending outward, without encountering the other exterior through normal space. Between them lies the bridge. On a carefully selected spatial slice, the geometry resembles two wide regions joined by a throat. This is the Schwarzschild wormhole, also called an Einstein-Rosen bridge in its standard modern interpretation. The diagram also contains a black hole region in the future and a white hole region in the past. The black hole interior accepts matter and light from either exterior, but it does not release them again. The white hole interior releases matter and light into the exterior regions, but nothing can enter it from outside. A white hole is not an ordinary black hole running backward like a film played in reverse. It is the time-reversed mathematical solution. To exist as part of the eternal geometry, it must already be present in the past. It cannot be formed simply by collapsing a star in the usual way, because collapse produces a future black hole region rather than a past white hole region. No confirmed white hole has been observed. Its presence in the maximal Schwarzschild extension reflects the demand that the idealized solution be continued as fully as the equations allow. Mathematics can include regions that are not produced by realistic astrophysical history. The bridge is widest at a particular moment that can be chosen as the time-symmetric middle of the eternal solution. Before that moment, the geometry can be viewed as expanding from the white hole region. After it, the throat contracts toward the black hole singularity. There is no interval during which a signal can leave one exterior, cross the throat, and reach the other. A light ray moves along the fastest causal path available, yet even light entering from one side is carried into the black hole region before it can emerge elsewhere. Matter, which must move more slowly than light locally, has no better chance. The phrase "closes too soon" can sound as though the traveller merely needs better timing. Perhaps one could wait until the throat reaches maximum width, start the engines at precisely the right instant, and rush through before the door shuts. The causal diagram rules out that plan. The failure is not caused by a slow spacecraft or an unfortunate departure schedule. No future-directed causal path connects the two exterior regions through the bridge. Fuller and Wheeler's analysis show that the Schwarzschild throat pinches off in finite time, trapping attempted signals rather than allowing communication between the two exterior regions. Imagine two runners on opposite sides of a drawbridge. In an ordinary situation, the question is whether the bridge remains down long enough for one runner to cross. In the Schwarzschild geometry, the more accurate picture is that every allowable route across the bridge turns toward a different destination. Running faster cannot fix a road whose future direction does not lead to the far bank. The distinction appears clearly in light cones. At every event in spacetime, a light cone marks the possible directions that light can travel. Paths taken by matter must remain inside that cone. Outside the horizon, the cones tilt toward the black hole, but still include directions that move outward. At the horizon, the outward edge lies along the boundary. Inside, all future directions point towards smaller radius. On a spacetime diagram, the singularity is not shown as a tiny point waiting at the centre. In the Schwarzschild interior, it appears as a future boundary stretching across the diagram. Once inside, reaching it is as unavoidable as reaching a later moment while sitting in an ordinary room. You can choose what to do before tomorrow arrives, but you cannot remain permanently in today. In a similar mathematical sense, an infalling observer can maneuver inside the horizon, but every future route still reaches the singularity. The observer cannot choose a future in the second exterior because that region lies outside the available light cones. This also explains why the wormhole cannot be crossed from the white hole side. A traveller in an exterior region cannot enter the white hole, because the horizon around that past region only permits signals to come outward. Entering it would require following a past-directed path, which is not an ordinary journey into the future. The complete Schwarzschild solution therefore has a connection without a usable passage. The two exteriors are part of one extended geometry, but they are causally separated. Neither side can send a message to the other through the wormhole. It is natural to ask whether the bridge exists at all if nothing can cross it. In geometry, connection and communication are different properties. A surface can be connected in a mathematical sense even when the spacetime's causal structure prevents an observer from travelling between its regions. Consider a map containing a river and a bridge that existed yesterday but collapsed before anyone set out today. The land on both sides still belongs to one mapped region. The historical structure may include the bridge, but the bridge does not provide a current route. The Schwarzschild case is stranger because the failure comes from space-time itself rather than damaged concrete. But the lesson is similar. Embedding diagrams add another source of confusion. These pictures take a two-dimensional slice of curved space and represent it as a surface bending through a higher dimensional flat space. The throat looks like a smooth tube connecting two funnels. Such a diagram shows spatial distances on one selected slice. It does not show horizons, light cones, or how the slice evolves. It is useful for visualizing curvature, but it cannot answer whether a traveler can pass through. For that, the time dimension must be restored. At the time-symmetric slice, the throat has a minimum radius equal to the Schwarzschild radius. The area of that spherical throat is finite. The spatial distance through the bridge can also appear finite. This makes the crossing look possible until the changing geometry is included. As the slices advance into the future, the connection narrows and disappears into the black hole singularity. Different choices of slicing can make the spatial evolution look different, because relativity does not provide a universal definition of space at the same moment across the entire geometry. Yet no change of slicing creates a causal route from one exterior to the other. Coordinate choices can alter the picture, but they cannot alter which events can influence which other events. The bridge also cannot be stabilized by simply placing a support at the throat. Any support is matter or energy, and matter or energy changes the space-time through Einstein's equations. Once a new stress-energy distribution is added, the result is no longer the unmodified vacuum Schwarzschild solution. This is an important rule in wormhole physics. Geometry is not a passive stage that can be reinforced without consequences. The reinforcement becomes part of the source of gravity and changes the geometry being reinforced. To hold a throat open, a model usually requires stress that resists gravitational collapse. Ordinary positive energy matter tends to focus bundles of light rays and encourage convergence. Traversable wormhole throats generally need the opposite behavior, which leads to violations of familiar energy conditions. The Schwarzschild wormhole contains no such supporting material. Outside the central singularity, it is a vacuum solution. Vacuum does not mean that spacetime is flat or empty of gravity. It means that the local stress-energy tensor vanishes. Curvature remains because the global geometry is associated with mass. Without special support, the throat is not a static doorway. Its maximum opening is only part of the eternal spacetime's geometry. The bridge contracts as the future black hole region develops, and the available causal paths terminate at the singularity. This produces another common misunderstanding. The wormhole does not begin as a long-lasting object and then suddenly suffer a mechanical collapse. There is no external clock watching a tunnel remain stable for several minutes before failing. The entire opening and closing pattern belongs to the four-dimensional solution from the start. General relativity describes the whole arrangement at once: the past white hole region, the two exteriors, the moment of maximum spatial connection, the future black hole region, and the singularities. Talking about the bridge opening and closing is a way of describing a sequence of spatial slices through that complete space-time. The eternal nature of the solution is crucial. The white hole and second exterior are not created when an ordinary black hole forms. They are already included in the maximally extended geometry. A black hole formed through stellar collapse has a different diagram. Before the star collapses, matter occupies the central region, and signals can move through the space where the horizon will later form. As collapse continues, an event horizon develops, and the singularity forms in the future. The space-time has one exterior corresponding to the surrounding universe. It doesn't contain the past white hole region of the eternal solution. and it does not automatically provide a second asymptotic exterior. This means the wormhole shown in the eternal Schwarzschild diagram should not be quietly placed inside every astrophysical black hole. The exterior geometry of a settled, spherical, non-rotating black hole may be described by the Schwarzschild metric, but the global interior history depends on how the object formed. Oppenheimer and Snyder's classic collapse model showed that a sufficiently massive star can continue contracting, with the collapse completed in finite time for an observer moving with the stellar material. The outside can look the same while the complete spacetime differs. This is possible because an observer outside the matter cannot recover every detail of the interior history from the static exterior field alone. Birkhoff's theorem helps explain the simplicity. Any spherically symmetric vacuum region is locally described by the Schwarzschild solution, even if matter elsewhere is moving. A spherical star can pulsate or collapse, while the vacuum geometry outside its surface retains the Schwarzschild form associated with its total mass. As the star shrinks through its Schwarzschild radius, the exterior horizon and black hole region emerge in the complete spacetime. Nothing in that process creates a second universe, joined by a traversable tube. The two-sided bridge belongs to the eternal extension, not to the ordinary one-sided collapse geometry. Could two black holes somehow be connected anyway? Classical general relativity permits many global arrangements, but producing a stable connection introduces new difficulties. A bridge joining separate exteriors would need initial conditions that create the right topology, and it would still be non-traversable without a source of negative energy or another modification. Quantum gravity may change the central story. The classical singularity signals that general relativity is incomplete under extreme conditions. A successful quantum theory of gravity might replace the singularity with a bounce, a transition, a highly quantum region, or something that current language cannot describe accurately. Some models explore black holes that transition into white holes or connect to additional regions after quantum corrections become important. These proposals are active areas of research, not established features of observed black holes. They should not be confused with the classical Schwarzschild wormhole, whose behavior is fixed by the unmodified equations. Hawking radiation introduces another long-term effect. Quantum fields around a black hole allow it to lose mass very slowly. For an astrophysical black hole, the evaporation time is enormously longer than the current age of the universe. The radiation does not hold the classical Einstein-Rosen bridge open, and it does not create a known exit into a second exterior. In fact, combining black holes with quantum information makes the situation more complicated. Physicists ask how information about infalling matter is represented in Hawking radiation, whether the interior is smooth, and how entanglement changes during evaporation. Wormhole ideas sometimes appear in those discussions, but the classical Schwarzschild bridge remains non-traversable. There is one modern method that can make a related two-sided geometry traversable under carefully controlled theoretical conditions. By introducing a suitable interaction or negative energy effect, the horizon can shift enough to let a signal pass. This does not reveal that the original Schwarzschild bridge was secretly open. It creates a modified spacetime with different matter content or boundary conditions. The distinction is similar to converting a sealed wall into a doorway. The finished doorway may occupy the same location, but construction has changed the structure. One cannot point to the doorway afterward and claim that the original wall was always passable. Any attempt to turn the Schwarzschild wormhole into a usable passage must therefore answer several questions. What provides the negative energy? How much is required? Can the effect remain stable? What happens when a traveller's own mass enters the throat? Does that added energy cause collapse? Can radiation pass safely? Are the two mouths accessible from the same universe? Back reaction is especially important. A test particle is an idealization whose mass is assumed too small to alter the geometry. A real spacecraft has energy and gravity. When it enters a delicate wormhole, its presence changes the space-time. a throat that remains open for an infinitesimal signal may close when asked to carry anything larger. The standard Schwarzschild bridge fails before those engineering questions even arise. Its causal structure blocks the crossing for light itself. There is no need to calculate passenger comfort, fuel requirements, or the recommended quantity of tea for the journey. The route is unavailable at the most basic level. Turning a Schwarzschild black hole into a traversable configuration requires adding new sources to the equations. Published constructions have used idealized negative energy radiation, while broader traversable wormhole work has tied the problem to difficult questions concerning energy conditions, quantum fields, and causality. This failure makes the Schwarzschild wormhole a useful reference point. Every traversable proposal can be compared with it. Does the new model remove the event horizon? Does it prevent the throat from pinching off? Does it replace the vacuum with special stress energy? Does it change the topology, or only the causal structure? Does it remain open after disturbances? It also clarifies why a black hole and a wormhole are not interchangeable terms. A black hole is defined by an event horizon, and a region unable to communicate with distant future infinity. A wormhole is a geometric connection between regions. One spacetime can have both, as the eternal Schwarzschild solution does, but the presence of a wormhole does not automatically provide escape from the black hole. The Schwarzschild case is highly symmetric. It has no preferred direction, no rotation axis, and no electric field. That symmetry makes its logic unusually clear. Enter the future horizon, and every route ends at the singularity. Look for a path to the other exterior, and none lies inside the future light cones. Changing the assumptions changes the internal map. Adding electric charge introduces an outer horizon and an inner horizon. The singularity takes a different form, and the maximal extension contains repeated regions connected in a more complicated pattern. On paper, those charged solutions appear to offer routes unavailable in Schwarzschild spacetime. A traveller may seem able to pass beyond the outer horizon, avoid a space-like singularity, cross an inner horizon, and enter another exterior region. That possibility is accompanied by serious instability. Radiation becomes enormously amplified near the inner horizon, and the neat extended diagram may not survive realistic disturbances. Even so, charge shows exactly how sensitive wormhole structure can be to the properties assigned to a black hole. Electric charge changes the interior map before it changes anything a distant observer is likely to notice. From far away, a Reissner-Nordstrom black hole still appears as a dark, spherical object. It does not rotate, and its mass remains the main influence on the motion of neutral bodies at large distances. Closer to the centre, however, the electric field contributes to spacetime curvature, and the simple Schwarzschild arrangement separates into a more complicated sequence of horizons and regions. The solution is named after Hans Reissner and Gunnar Nordstrom, who independently found charged, spherically symmetric solutions during the early development of general relativity. The model assumes a black hole with mass and electric charge, but no rotation. This makes it less simple than Schwarzschild spacetime and less realistic than a rotating black hole, yet it remains valuable because charge changes the geometry without removing spherical symmetry. The mathematics contains a term associated with mass and another associated with charge. Far from the black hole, the mass term dominates. Nearer the centre, the charge term becomes increasingly important because it changes more rapidly with distance. This does not mean electric repulsion simply defeats gravity in the ordinary Newtonian sense. The electromagnetic field has energy, that energy gravitates, and the combined Einstein-Maxwell equations determine the final geometry. Three broad cases appear depending on the relationship between charge and mass. In the first case, the charge is below a critical value. The spacetime has two horizons, an outer one and an inner one. This is called a sub-extremal Reissner-Nordstrom black hole. In the second case, charge reaches the critical value and the two horizons coincide. That limiting object is called extremal. In the third case, the charge is larger than the allowed black hole limit. No horizon forms, leaving the central singularity exposed. This is the super-extremal case, usually described as a naked singularity rather than a black hole. The sub-extremal case gives us the wormhole-like structure. Its outer horizon behaves much like the event horizon of a Schwarzschild black hole. Once a traveller crosses it inward, returning to the original exterior is no longer possible. The difference appears deeper inside, where a second boundary waits. That second boundary is called the inner horizon, or Cauchy horizon. It changes the causal structure in a way the Schwarzschild solution never permits. In the ideal, exact geometry, passing the inner horizon can lead into another region where the radial direction behaves differently. Instead of being forced directly into a space-like singularity, a carefully chosen path may appear able to avoid the singularity and continue toward another exterior universe. This is the charged gateway that makes the maximally extended Reissner-Nordström diagram so tempting. On paper, the spacetime does not stop after one black hole interior, it repeats. Exterior regions, black hole regions, white hole regions, and additional exteriors form an extended chain. A traveller entering from one exterior can trace a possible path through the outer horizon, across the inner horizon beside the singularity, and outward into another region. The phrase, beside the singularity, needs precision. The singularity in Reissner-Nordström spacetime differs from the Schwarzschild singularity. In the Schwarzschild case, the singularity is space-like. Once the horizon has been crossed, it lies across the traveller's future in much the same way a later moment lies ahead in ordinary time. Avoiding it is not an available option. The charged solution has a time-like singularity in its ideal maximal extension. On a causal diagram, it behaves more like a place than a final moment. A world line can, mathematically, pass alongside it rather than ending there. This is what opens the apparent route to another region. Calling that route a wormhole is reasonable, but it is not a stable, horizon-free tunnel with two convenient entrances. The traveller must cross an event horizon, enter a black hole interior, approach an inner horizon, and rely on the exact continuation of an idealized space-time. The destination is not selected by pointing the mouth toward a planet. It is another asymptotically flat region contained in the maximal mathematical extension. Ray tracing studies of that extension can follow ideal paths through the interior and into its additional regions, but the exercise begins with the exact unperturbed solution. A distant observer in the starting exterior cannot follow the traveller's signals indefinitely. Light sent outward after the event horizon crossing cannot return through the outer boundary. From the traveller's perspective, the local journey continues, but communication with home ends. Inside the outer horizon, the radial coordinate again takes on a time-like role. Moving toward the inner horizon becomes unavoidable for future-directed motion, just as moving toward the Schwarzschild singularity was unavoidable in the uncharged case. The major difference is that the inner horizon is not the final boundary in the exact solution. Crossing it enters a region where the radial coordinate becomes spatial again. The traveller may then manoeuvre in ways that were impossible between the horizons. The time-like singularity remains dangerous, but it does not occupy the entire future. A suitable path appears capable of turning away from it. Continue far enough through the ideal diagram, and another horizon can be crossed outward. The traveller then enters a new exterior region. That exterior may resemble the universe left behind, but it is not the same exterior reached by taking a normal route through space. In the complete mathematical extension, it is a separate asymptotic region. There is no single final destination. The pattern repeats upward and downward in the standard causal diagram. Additional black hole and white hole regions connect additional exterior universes. The result resembles a vertical stack of diamond-shaped regions, with passages linking one section to the next. This repeated structure is sometimes described as an infinite tower of universes. The phrase is dramatic, but it represents the way the exact solution continues mathematically. It does not establish that real charged black holes manufacture an endless supply of inhabited cosmoses. The diagram shows what follows when the ideal metric is extended without disturbances, and classical general relativity is trusted wherever the equations remain regular. Even before instability is considered, the model makes demanding assumptions. The black hole must be perfectly spherical, exactly non-rotating, and described by a fixed electric charge. No infalling radiation, no stray particles, no gravitational waves, and no uneven collapse are allowed to disturb the interior. The traveller is also treated as too insignificant to alter the geometry. That last assumption is particularly awkward for a gateway. A wormhole intended to carry matter must respond to the matter being carried. A spacecraft has mass, energy, electric charge, radiation, and gravitational influence. Treating it as a test object is useful for drawing a path, but a realistic crossing must include its back reaction. Charge creates another practical problem long before anyone reaches the inner horizon. A strongly charged black hole attracts particles with the opposite electric charge and repels particles with the same sign. In an environment containing plasma, this tends to reduce a large net charge. Studies of charged black hole neutralization find that oppositely charged particles have a greater probability of falling inward, making strongly charged astrophysical black holes difficult to maintain. A small residual charge may still be possible, and charge can influence the motion of nearby particles even when it is tiny compared with the black hole's mass. The ideal Reissner-Nordström geometry remains useful as a model. However, the near-extremal charge required to make some of its unusual features especially prominent is not something an ordinary black hole surrounded by charged matter would preserve easily. The most serious problem waits at the Cauchy horizon. To understand it, we need to ask what that name means. A Cauchy surface is a slice through space-time on which complete information can, in principle, be specified so that the laws of physics determine what happens throughout the region controlled by that data. This is the normal predictive structure expected from classical physics. Give the positions and motions of the relevant objects, along with the fields, and the equations provide their evolution. A Cauchy horizon marks the limit of the region that can be predicted from that initial information. Beyond it, the earliest data may no longer be sufficient to determine a unique continuation. The maximally extended Reissner-Nordström solution can be continued through the inner horizon, but the continuation is not controlled in the same globally predictable way by data from the original exterior. This makes the inner horizon conceptually unusual and physically suspicious. General relativity values smooth solutions, but physics also relies on predictability. If small changes in initial conditions produce enormous or undetermined changes beyond a boundary, the exact solution may not describe what a real system becomes. Radiation approaching an inner horizon is exposed to an extreme blue shift. Blue shift is an increase in the frequency and measured energy of incoming waves. It is the opposite of redshift. Near the outer event horizon, signals sent outward can become increasingly redshifted for distant observers. Near the inner horizon, the causal arrangement produces the reverse danger. Radiation falling into the black hole can pile up and appear at progressively higher frequencies to an observer approaching the Cauchy horizon. No real black hole is perfectly isolated. Light, gravitational radiation, stray particles, and the fading disturbances left from collapse remain present. Even when the incoming radiation becomes extremely weak at late times, the inner horizon can amplify it through enormous blue shift. A faint stream of radiation outside can become a severe gravitational problem inside. The effect is not merely that a traveller sees a bright flash. Radiation carries energy, and its energy contributes to space-time curvature. As the measured energy grows, it alters the geometry that originally allowed the inner horizon to exist. Eric Poisson and Werner Israel developed this process into the mass inflation model. Their work showed that interacting ingoing and outgoing radiation near the inner horizon can drive the effective internal mass parameter and the curvature toward classically unbounded values, the inner horizon that appeared smooth in the exact Reissner-Nordström solution becomes unstable once realistic perturbations are included. The word inflation here does not mean the cosmic inflation thought to have occurred in the early universe. It refers to the rapid growth of the internal mass function. The black hole's mass as measured from far outside does not suddenly become infinite. The divergence belongs to the interior description near the Cauchy horizon. Imagine two streams crossing, one moving inward and another moving outward. Each stream sees the other at an increasingly high relative energy. Their combined gravitational effect grows, and the exact quiet inner horizon cannot remain quiet under that traffic. This is a recurring lesson in relativity. A structure may exist perfectly in a symmetric eternal solution and disappear when the smallest realistic disturbance is added. Symmetry can hide an instability in the same way a pencil can balance on its tip in a careful drawing. The position is mathematically allowed. A minor vibration reveals how little protection it has. Mass inflation can produce a curvature singularity along or near the inner horizon. The detailed strength and character of the singularity depend on the model, but the safe route shown in the undisturbed diagram is no longer reliable. More recent work examining perturbed, maximally extended Reissner-Nordström geometries found that collapse of the inner horizon prevents an observer from reaching the white hole and parallel universe regions. An observer who crosses the damaged inner horizon remains headed toward a central singularity rather than an exit. This does not mean every theoretical question about the inner horizon is settled. Researchers continue to examine how classical perturbations, quantum fields, evaporation, cosmological backgrounds, and modified theories of gravity affect Cauchy horizons. Different studies also use different mathematical standards for deciding whether a spacetime remains extendable. The simple travel conclusion remains cautious. The clean gateway of the exact Reissner-Nordström extension is not expected to survive ordinary disturbances in a form that a traveller could reliably use. The instability also connects to the strong cosmic censorship conjecture. Broadly stated, this idea suggests that physically reasonable initial conditions should not produce accessible regions where classical evolution loses uniqueness. Nature may prevent a usable Cauchy horizon by replacing it with a singular boundary. Cosmic censorship is not one simple rule that has been proved for every possible spacetime. It has several formulations, and precise statements depend on the matter involved, the surrounding geometry, and the degree of smoothness demanded from any extension. Reissner-Nordström interiors remain important test cases because their exact Cauchy horizons challenge the expectation of predictable evolution. If perturbations always destroy the horizon strongly enough, predictability is preserved at the cost of a singularity. If some weaker continuation remains possible, the conjecture must be stated more carefully. Either result is interesting to physicists and mathematicians, although neither is helpful to a passenger approaching the inner horizon with luggage. The extremal case introduces a different arrangement. When the charge reaches the critical value, the outer and inner horizons meet. Instead of two separate boundaries, the exact geometry contains one degenerate horizon. The term degenerate does not mean poorly designed. It means the mathematical route defining the horizon is repeated. The horizon's surface gravity becomes zero in the classical solution, and the geometry develops a long throat-like region. From the outside, it remains an event horizon. It does not become a traversable mouth. The merged boundary changes the causal diagram, but it does not offer a route through which a traveller can enter and later return to the same exterior. Extremal black holes are useful in theoretical physics because they often have special symmetries and simplified properties. They appear in studies of quantum gravity, string theory, black hole entropy, and the relationship between geometry and quantum states. Exact extremality is also finely balanced. Add an ordinary neutral particle, and the mass changes. Add a charged particle, and both mass and charge may change. radiation and quantum processes can move the object away from the ideal relationship. One might try to add enough charge to move beyond the extremal limit. In the classical equation, the horizons then vanish. This produces the super-extremal Reissner-Nordström geometry. Without a horizon, the central time-like singularity is exposed to the exterior. Light or particles from near it can, at least in the ideal geometry, travel outward to distant observers. This is called a naked singularity. A naked singularity is not a more convenient wormhole. Removing the horizons also removes the repeating black hole and white hole passage structure. What remains is an exposed failure of the classical description. The weak cosmic censorship conjecture is often expressed as the expectation that realistic collapse does not produce naked singularities visible from far away under ordinary conditions. It is tempting to imagine that electric repulsion might hold a wormhole open. Charge can oppose collapse in some physical systems, and an electric field certainly changes the Reissner-Nordström horizon structure. It does not, by itself, create a stable, horizon-free, safely traversable tunnel in the standard solution. The apparent route still passes through a black hole event horizon and depends on the survival of an inner Cauchy horizon. Once that boundary becomes unstable, the exit is lost. Charge has replaced the unavoidable Schwarzschild singularity with a mathematical route whose most important junction cannot tolerate realistic traffic. There is another subtlety in the phrase, another universe. In these diagrams, a universe often means an asymptotically flat exterior region. It does not necessarily mean a region with a separate Big Bang, different physical laws, unfamiliar matter, or a civilization waiting beside the exit with a welcome sign. Two asymptotic regions can belong to one connected spacetime while remaining impossible to reach from each other through the ordinary exterior. Calling them separate universes is useful, but it can make the picture sound more definite than it is. The mathematical statement concerns separate exterior regions. The physical question is whether the global structure can form and remain stable. The maximal extension also includes white hole regions for the same reason the eternal Schwarzschild solution did. The equations have been continued both forward and backward as far as the ideal geometry permits. An ordinary charged black hole formed through collapse does not begin with the complete eternal tower already assembled. A realistic collapse diagram therefore differs from the eternal one. Charge matter falls inward, horizons form, and disturbances accompany the process. The inner region may initially resemble portions of Reissner-Nordström spacetime if the object carries enough charge, but the Cauchy horizon instability changes what follows. This distinction prevents a common shortcut in reasoning. Finding a path on an eternal diagram does not show that a traveller entering a physically formed black hole will follow it. The traveller moves through the spacetime produced by actual initial conditions, including radiation and back reaction, not through whichever exact extension provides the most attractive route. There is no observational evidence for a Reissner-Nordström wormhole, an infinite tower of exterior regions, or an astrophysical black hole holding the near-extremal electric charge required by the cleanest versions of the geometry. Charged black hole models can still be used to calculate possible effects on nearby particles and fields, but plasma, magnetic fields, and rotation make the astronomical setting much less tidy. The model earns its place because it shows how one additional physical property transforms an entire interior. Schwarzschild spacetime has one horizon and a space-like singularity. A sub-extremal Reissner-Nordström spacetime has an outer horizon, an inner horizon, and a time-like singularity. Its maximal extension appears to permit repeated passages into new exterior regions. Perturbations then reveal that the crucial inner route is unstable. That pattern becomes even more important when angular momentum replaces electric charge. Rotation is not an unusual theoretical decoration. Stars rotate. Collapsing matter carries angular momentum, and the black holes produced by real astronomical processes are expected to spin. The charged solution has already supplied the warning we will need. An attractive path in an exact diagram may pass through the least stable part of the spacetime. Rotation removes the last trace of spherical simplicity. A charged black hole can still be described as the same in every direction, but a spinning black hole has an axis, an equator, and a preferred direction of motion. Space and time near it are no longer curved in a perfectly even pattern. They are dragged around the rotating mass, forcing light, matter, and even stationary observers to take part in the motion. This makes the Kerr solution more complicated than the Schwarzschild and Reissner-Nordström geometries. It also makes it more relevant to the real universe. Stars rotate, clouds of gas rotate, galaxies rotate. When matter collapses to form a black hole, its angular momentum does not simply disappear. The resulting object is expected to spin unless some highly effective process removes nearly all of that rotation. Roy Kerr found the exact vacuum solution for a rotating mass in 1963. His result describes a stationary, axisymmetric black hole characterized by its mass and angular momentum. It became one of the central solutions of general relativity because it provides the basic exterior geometry expected around an isolated rotating black hole. Stationary means that the geometry does not change with time in the chosen description. Axisymmetric means that it remains unchanged when rotated around one particular axis. It is not the same in every direction, but it is the same at every angle around the spin axis. A Kerr black hole is often described using a parameter called A, related to the angular momentum divided by the mass. Physicists also use a dimensionless spin parameter that compares the angular momentum with the maximum value permitted for a black hole of that mass. A non-rotating object has zero spin and reduces to the Schwarzschild solution. As the spin increases, the geometry becomes more strongly distorted. Below the extreme limit, the Kerr solution has two horizons. The outer horizon is the event horizon, the boundary beyond which no future-directed signal can return to the distant exterior. The inner horizon is a Cauchy horizon, similar in its basic role to the inner horizon of the charged Reissner-Nordström solution. The exact positions of the horizons depend on the mass and the spin. As rotation increases, the outer and inner horizons move closer together. At the extremal limit, they meet. Beyond that limit, the equations contain no horizon, and the central singularity is exposed. The event horizon of a Kerr black hole is not a rigid surface spinning through space like a metal sphere. It is a null boundary in space-time. Still, the rotation affects everything nearby, and the influence extends beyond the horizon into a region called the ergosphere. The outer edge of the ergosphere is known as the stationary limit. It touches the event horizon at the poles and bulges outward around the equator. Between the stationary limit and the horizon, remaining fixed relative to distant stars is impossible. An observer can resist falling inward for a time, depending on the location and available acceleration, but cannot remain completely motionless with respect to infinity. Space-time itself is dragged in the direction of the black hole's rotation. Every possible future path turns around the axis. This effect is called frame dragging. It occurs around any rotating mass, including Earth, although the effect around Earth is extremely small. Around a rapidly spinning black hole, it dominates the available motion near the horizon. Frame dragging does not mean that space behaves like an ordinary fluid being stirred by a spoon. The comparison is useful only up to a point. What changes is the relationship between coordinates, inertial motion, and the directions available to light and matter. A spacecraft entering the ergosphere would find that maintaining a fixed angular position required moving faster than light. Since that is impossible, the craft must rotate with the black hole. It can still fire its engines and choose among different trajectories, but standing still is no longer one of the options. The ergosphere also allows rotational energy to be extracted. In the Penrose process, an object entering the ergosphere splits into two parts. One part falls into the black hole along a trajectory that has negative energy when measured relative to infinity. The other part escapes with more energy than the original object carried. The additional energy comes from the black hole's rotation. Its angular momentum decreases slightly as a result. Related electromagnetic mechanisms are considered important in explaining how spinning black holes may power enormous astrophysical jets. None of this creates a wormhole by itself. The exterior rotation provides energy and unusual paths, but the wormhole-like structure appears only when the exact Kerr spacetime is extended through its horizons and into its deeper mathematical regions. The first boundary encountered by an infalling traveller is the outer event horizon. Like the Schwarzschild horizon, it is a one-way causal boundary. Once crossed inward, no ordinary future-directed route returns to the original exterior. The local crossing may not involve a sudden impact. A sufficiently large black hole can have modest tidal forces at the outer horizon. The traveller's instruments would still detect important changes in the surrounding light and geometry, but there is no solid surface marking the point of no return. Between the outer and inner horizons, the radial direction again becomes tied to the traveller's future. Every allowed path proceeds toward the inner horizon. Rotation adds sideways motion and changes the exact trajectories, but it does not restore an outward route to the original universe. The inner horizon is where the ideal Kerr extension begins to offer possibilities that the Schwarzschild solution does not. In the exact unperturbed geometry, a traveller can cross the Cauchy horizon and enter another region where the radial coordinate becomes spatial again. Beyond that boundary lies the feature most strongly associated with the Kerr interior, a ring singularity. The Schwarzschild singularity is located at zero radius and forms a space-like future boundary. The Kerr singularity is not a single point in the geometry. In commonly used coordinates, it forms a ring in the equatorial plane. The size of the ring is related to the black hole's angular momentum. When the spin goes to zero, the Kerr solution reduces to Schwarzschild spacetime, and the ring description no longer applies in the same way. Approaching the ring itself is not a safe method of crossing anything. Curvature becomes singular there, and analyses of nearby geodesics find destructive tidal behaviour for observers that approach the singular set. A ring, however, has an opening through its centre. This leads to one of the most unusual features of the maximal Kerr extension. In the exact geometry, certain paths can pass through the equatorial disk bounded by the ring without striking the singular ring itself. Continuing through that disk takes the path into a region commonly described using negative values of the radial coordinate. The word negative does not mean that the traveller has moved to a distance less than nothing, in an ordinary physical sense. It labels a new portion of the extended geometry. Far into this negative radius region, the space-time can approach another asymptotically flat exterior. From the mathematical viewpoint, the Kerr solution therefore appears capable of connecting different sheets or exterior regions. This is the basis for calling the Kerr extension a wormhole. A route seems to pass through the interior of the rotating black hole, avoid the ring singularity, and continue into another region rather than ending at the central boundary. Brandon Carter's analysis of the Kerr family helped establish the global structure of these extended rotating spacetimes and the additional regions obtained by continuing the solution through its horizons. The full extension is far more complicated than a single doorway between two places. Like the charged solution, it can contain a repeated sequence of exterior regions, black hole interiors, white hole interiors, inner horizons, and further asymptotic areas. A traveller following a carefully selected geodesic in the exact diagram may pass from an original exterior through the outer horizon, cross the inner horizon, move around the ring singularity, and emerge into another section of the extension. Some diagrams suggest more than one possible exit. The traveller's route depends on energy, angular momentum, direction of approach, and the inclination relative to the equatorial plane. rotation prevents the motion from being reduced to a simple inward or outward line. Particles and light can orbit, spiral, cross the equatorial plane, or approach the inner structure from different angles. The equations of geodesic motion contain several conserved quantities, including a quantity identified by Carter that allows the motion to be separated and calculated. This mathematical order is impressive. It does not make the journey physically reliable. The first problem is that the maximal Kerr extension is an eternal exact solution. It assumes the rotating black hole has always existed in that ideal form. It includes past white hole regions and repeated exteriors that do not automatically arise when a rotating star collapses. An astrophysical black hole forms from matter. The collapse produces radiation, uneven density, magnetic fields, gravitational waves, and continuing streams of material. Even after the object settles externally toward the Kerr form, its interior remembers that it formed through a dynamic process. The exterior may become remarkably simple. According to the black hole uniqueness results, often summarized by the phrase "no hair," a settled black hole in standard general relativity is described externally by mass, angular momentum, and electric charge. Since large electric charge is expected to neutralize readily, mass and spin should dominate most astrophysical cases. A simple exterior does not guarantee that the entire maximal analytic extension exists inside. The external field can approach Kerr geometry, while the inner horizon and regions beyond it are changed completely by the black hole's formation and continuing accretion. The second problem is the same weakness encountered in the charged solution. The apparent route to another exterior depends on crossing the inner Cauchy horizon. That horizon is unstable to radiation and perturbations. Light and gravitational disturbances falling inward become extremely blue-shifted as they approach it. Outgoing radiation left from the collapse can meet incoming radiation at enormous relative energies. Each stream measures the other as becoming more energetic. Their gravitational interaction changes the geometry. The internal mass parameter grows rapidly, and curvature can rise without limit in the classical calculation. Poisson and Israel connected this mass inflation mechanism directly with rotating collapse, noting that the radiative tail produced by the collapse becomes infinitely blue-shifted at the inner horizon. Their analysis showed that this can drive the effective interior mass and curvature to classically unbounded values, while leaving the exterior mass finite. This is not a small disturbance added to an otherwise usable gateway. The unstable surface is the gateway's main junction. Every proposed route into the additional Kerr regions relies on the inner horizon remaining regular enough to cross. Realistic black holes cannot be isolated from all disturbances. The background universe supplies radiation, accretion supplies particles. The collapse that created the black hole supplies decaying gravitational and electromagnetic fields. A traveller also supplies mass and energy. Even a tiny incoming disturbance can become important after sufficient blue shift. The ideal Kerr diagram assumes exactly the level of calm that the inner horizon is least able to tolerate. Detailed studies of accreting rotating black holes find that hyperrelativistic counterstreaming near the inner horizon triggers mass inflation and is followed by further collapse of the interior geometry. Numerical work has indicated that this process can develop into a space-like singularity, removing the clean route through the repeated Kerr regions. The exact final structure remains an area of research because solving the full nonlinear equations inside a rotating black hole is extremely difficult. Quantum gravity should become important once curvature reaches sufficiently high values. General relativity cannot confidently describe what happens beyond that regime. The safe conclusion is not that a different universe definitely lies behind every spinning black hole. The safe conclusion is that the ideal Kerr solution contains extended regions and apparent paths, while realistic perturbations are expected to destroy the smooth, inner horizon route before it can function as a dependable passage. The third problem appears after the ring is avoided and the negative radius region is entered. Parts of that extended geometry contain closed time-like curves. A time-like curve represents a possible path for an object moving more slowly than light. A closed time-like curve returns to an earlier event on its own path. In ordinary language, it provides a form of travel into the past. Near parts of the Kerr ring structure, the coordinate direction around the axis can become time-like. Travelling around the black hole in the right region could, in the exact mathematics, bring an observer back to their own past. This creates the usual causality problems. A traveller might influence the conditions that led to the journey. A message could arrive before it was sent. A sequence of events might become its own cause. Closed time-like curves are not unique to Kerr spacetime. They appear in several exact solutions of general relativity. Their existence in an equation does not show that nature permits them to form in accessible regions. The causality-violating region in Kerr lies beyond the event horizon and inner horizon, close to a singular structure whose stability is already doubtful. It is not an area that can be approached from the exterior and inspected safely. The fourth problem concerns negative mass. In parts of the traditional extended Kerr description, the asymptotic region reached through the ring can be interpreted as having unusual mass properties relative to the original exterior. The global interpretation of the negative radius sheet is subtle, and aspects of the standard maximal extension have been debated. What matters for the present journey is that the far side is not simply another ordinary location in our own universe connected by a neat, stable throat. The geometry contains horizons, singular behaviour, possible causality violations, and additional sheets defined by analytic continuation. It is a mathematical extension of a vacuum solution, not an engineered transport network. A traveller would also have no simple control over where the route emerges. The destination is set by the global geometry and the selected world line. There is no movable second mouth waiting near a chosen star. This makes the phrase Kerr wormhole very different from the traversable wormholes usually imagined in science fiction. A traversable wormhole should have two accessible mouths. A traveller should be able to enter one without crossing a destructive event horizon, pass through a stable throat, and emerge from the other. The Kerr passage begins by requiring entry into a black hole. Communication with the original exterior ends at the event horizon. The journey then depends on an unstable Cauchy horizon and passes near a ring singularity. Even the ideal exit belongs to an additional analytic region rather than a controlled destination. Rotation does provide one advantage over the Schwarzschild case. The classical singularity no longer blocks every future path in the exact solution. Because the singularity is ring-shaped and time-like, some mathematical trajectories can avoid it. That is a meaningful difference. It explains why Kerr spacetime has a richer maximal extension, and why rotating black holes became associated with passages to other regions. Avoiding one singularity does not guarantee surviving the rest of the interior. The route still passes through a region where perturbations are amplified so severely that the smooth extension is not expected to remain intact. Extremal Kerr geometry adds another variation. As the spin approaches the maximum allowed value, the outer and inner horizons approach each other. At exact extremality, they coincide. The near horizon region develops a long geometric throat and enhanced symmetry. This makes extremal and near-extremal Kerr black holes useful in studies of black hole thermodynamics, quantum gravity, holography, and particle acceleration. The extremal throat is not an open wormhole mouth. It remains associated with an event horizon. A traveller crossing inward cannot return to the original exterior. Reaching exact extremality may also be physically difficult. Accreting matter can increase a black hole's spin, but radiation from an accretion disk exerts a counteracting effect. In a classic calculation, Kip Thorne found a limiting dimensionless spin of roughly 0.998 for an ideal thin disk accretion process rather than the exact value of 1. That limit is not universal for every imaginable accretion flow, merger, or magnetic environment. It shows that realistic processes can prevent a black hole from reaching the exact extremal state, even when incoming matter carries large angular momentum. Trying to push the spin above the extremal limit produces a super-extremal Kerr solution. The horizons disappear, leaving the ring singularity naked. As with an overcharged Reissner-Nordström object, this does not create an improved gateway. It exposes a singular region and introduces accessible causality problems. The cosmic censorship conjecture suggests that physically reasonable collapse should not produce such naked singularities, although the conjecture has not been established in every possible setting. Attempts to overspin a black hole by sending in carefully chosen matter usually encounter compensating effects. The object's energy, angular momentum, radiation, and self-force must all be included. A calculation that treats the incoming body as a negligible test particle can appear to cross the limit, while a more complete calculation may restore the horizon. The Kerr solution is nevertheless strongly connected with observation. The Event Horizon Telescope images of M87 star and Sagittarius star show bright ring-like emissions surrounding a central dim region. Comparisons with relativistic simulations are consistent with the expected appearance of Kerr black holes, although the images do not reveal the internal maximal extension or prove the existence of any wormhole route. Astronomers also estimate black hole spin using X-ray spectra, the shapes of emission lines, the thermal emission of accretion disks, and the behavior of relativistic jets. These methods study matter outside the event horizon. They provide information about the exterior spacetime and the innermost stable orbits, not direct access to the ring singularity or inner horizon. Gravitational wave observations add another test. When two black holes merge, the final object settles through a pattern of vibrations called ring down. The frequencies and decay rates depend on the mass and spin. Current observations agree broadly with rotating black hole predictions, while future detectors should test the Kerr description more precisely. None of these measurements can show whether the ideal repeated interior regions exist. The event horizon prevents information from the black hole interior from reaching distant observers through ordinary causal paths. A Kerr black hole can therefore be observationally Kerr-like outside, while its deep interior differs from the eternal analytic extension. This separation between exterior success and interior uncertainty is essential. The exterior solution is one of the greatest achievements of general relativity. It explains frame dragging, rotating horizons, orbital motion, and many properties of accreting black holes. The maximally extended interior is a mathematically valid continuation of the exact solution. Its use as a wormhole is another matter. The path is hidden behind an event horizon, routed through an unstable Cauchy horizon, placed near a destructive ring singularity, and directed toward regions with severe causal and interpretive problems. A traveller entering the ergosphere may extract energy and escape if the trajectory remains outside the event horizon. A traveller crossing the event horizon has committed to the interior. Any promise of another exterior depends on the ideal geometry surviving conditions under which it is known to be unstable. This leaves the Kerr wormhole in a curious position. It is more relevant to real black holes than the charged Reissner-Nordström gateway, because astrophysical black holes are expected to spin. At the same time, its apparent passage depends on features that are unlikely to survive realistic formation and accretion. The repeated failure of black hole wormholes suggests that the problem is not simply choosing the correct type of black hole. Schwarzschild geometry closes the bridge too quickly. Charge introduces an inner route that suffers mass inflation. Rotation produces a ring that can be avoided mathematically, but the same inner horizon instability remains. A genuinely usable wormhole needs a different design. Its mouths must be accessible without entering a one-way black hole region. The throat must remain open while light and matter cross it. Tidal forces must be kept within survivable limits, and any supporting energy must respond consistently when the traveller enters. Those requirements seem reasonable. They're also severe enough to change the problem completely. Instead of beginning with a known black hole solution and asking whether its interior contains an escape route, physicists can begin with the conditions required for travel and ask what space-time geometry would satisfy them. This reverses the usual procedure. The destination is selected first, and Einstein's equations are then used to determine what kind of matter and energy would be needed to produce it. That was the approach taken by Michael Morris and Kip Thorne in a widely influential 1988 paper. Their goal was partly educational. They wanted to use wormholes to teach the methods of general relativity, while investigating whether the laws of physics could permit rapid interstellar journeys. The work was also connected with Carl Sagan's novel Contact. Sagan wanted the story's travellers to cross interstellar distances in a scientifically defensible way, and discussions with Thorne helped move the fictional mechanism away from an ordinary black hole and toward a traversable wormhole. Morris and Thorne then developed a general class of solutions intended, at least in principle, to allow a human traveller to pass through safely. These objects are commonly called Morris-Thorne wormholes. They also belong to the broader family of traversable Lorentzian wormholes. The word Lorentzian identifies the kind of geometry being used. Ordinary space-time has 3 spatial dimensions and 1 time dimension, and the time direction enters the measurement of space-time intervals differently from the spatial directions. This structure determines light cones, causal order, and which paths can be followed by matter or light. A Lorentzian wormhole is therefore not merely a curved 3-dimensional tunnel drawn on a page. It is a connection in a full space-time where clocks run, signals propagate, and travellers follow future-directed paths. The geometry must remain suitable not only on one spatial snapshot, but throughout the crossing. This separates Lorentzian wormholes from Euclidean wormholes, which appear in calculations where time has been replaced by a mathematical coordinate that behaves more like another spatial direction. Euclidean wormholes can be important in quantum gravity, but they are not automatically places through which a person can travel while watching a wristwatch continue to tick. Morris and Thorne considered a static, spherically symmetric geometry. Static means that its properties do not change with time. Spherical symmetry means that the geometry looks the same in every direction around its centre. These assumptions do not describe every possible traversable wormhole, but they provide the clearest starting point. Their metric contains 2 especially important functions. One is called the redshift function. The other is called the shape function. The redshift function controls how clocks and light behave at different positions. If it becomes infinite or develops the wrong behaviour, an event horizon can appear. A traversable wormhole must avoid that result. The redshift function therefore has to remain finite everywhere along the route. This is the first major improvement over a black hole wormhole. There is no one-way horizon blocking the entrance. Light can travel through the throat in both directions, and a traveller can, at least according to the geometry, enter one mouth and later communicate with the region left behind. The shape function determines the spatial form of the wormhole. It describes how the radial geometry narrows toward a minimum sphere and then expands again on the other side. That minimum sphere is the throat. The radial coordinate used in the metric behaves differently from an ordinary distance. It decreases as the traveller approaches the throat from one side, reaches a minimum value there, and increases after the traveller crosses to the other side. It does not continue downward through 0. For comparison, imagine walking along a narrow valley between 2 broad plains. Your altitude decreases as you approach the lowest point, then increases after you pass it. The lowest altitude does not mean the path ends. It marks the transition between the 2 slopes. The wormhole throat works in a similar geometric way, although the minimum quantity is the radius of a sphere rather than the height of a footpath. A traveller moving inward sees spheres around the centre become smaller. At the throat, the sphere has its minimum area. Beyond it, the surrounding spheres become larger again. The proper distance through the wormhole remains well behaved even though the radial coordinate reaches a minimum. This proper distance is what a ruler or traveller would measure locally along the route. It can extend smoothly from one exterior region, through the throat, and into the other. The shape function must satisfy a condition at the throat. Its value there equals the throat radius. It must also satisfy what Morris and Thorne called the flare-out condition. The geometry cannot simply narrow to a cylinder of constant radius, or continue collapsing into a black hole. It must open outward on both sides of the minimum surface. In the usual static spherical model, this condition requires the derivative of the shape function at the throat to be less than 1. An embedding diagram makes this easier to picture. Take a two-dimensional slice through the wormhole at one moment, usually through its equatorial plane. The resulting curved surface can be represented inside an imaginary three-dimensional flat space. Far from the throat, the surface may look nearly flat. Closer in, it bends downward into a broad funnel. Instead of ending, the funnel reaches a minimum radius and connects to a second funnel that opens outward toward another flat region. The two sides may represent distant locations in the same universe. They may also represent separate asymptotic regions. The local geometry near the throat does not decide the complete global interpretation by itself. Unlike the Schwarzschild embedding diagram, the Morris-Thorne picture is intended to describe a throat that remains open. The traveller does not have to race against a collapsing bridge. The connection is static unless the model is deliberately made time-dependent. Keeping the throat open is where the difficulty appears. Einstein's equations relate the selected geometry to a stress-energy tensor. That tensor describes the density of energy, the pressures, and the tensions required to produce the curvature. When Morris and Thorne inserted their wormhole geometry into the equations, they found that ordinary matter could not provide the required support at the throat. The radial tension had to be extraordinarily large. More importantly, that tension had to exceed the local mass-energy density in a way that violates familiar energy conditions. Their original analysis emphasized that no known material possessed the required relationship between tension and energy density. A tension is a negative pressure. A stretched cable is under tension because each part pulls on the parts beside it. In a wormhole, radial tension acts along the direction through the throat. Ordinary materials can withstand tension, but they also contain positive energy. There are limits to the relationship between their stress and energy density. Steel, carbon fibre and neutron star matter remain far from the behaviour needed to hold open a macroscopic Morris-Thorne throat. The required source is usually called exotic matter. The word does not identify a particular substance. It describes matter, or a field configuration, whose stress energy violates one or more of the energy conditions often imposed in general relativity. Energy conditions are not separate laws added to Einstein's equations. The equations themselves accept many mathematical stress-energy tensors. Energy conditions are assumptions intended to capture properties expected of physically reasonable matter. The null energy condition is especially important for wormholes. It states that the stress energy measured along any null direction should be non-negative. Null directions are the paths followed by light. For a static Morris-Thorne wormhole in ordinary general relativity, the flare-out condition implies that the null energy condition is violated near the throat. In suitable language, some observer or light-directed measurement encounters negative effective energy density. This result is not an inconvenient feature of one badly chosen example. It follows from the geometry required to make the throat flare outward. Normal positive energy matter tends to focus bundles of light rays. A traversable throat requires them to defocus enough to pass through the minimum surface and spread outward again. The focusing of light is described by the Richard-Hurry equation, which tracks how a family of nearby geodesics expands, shears and converges. Under the null energy condition, gravity tends to make null geodesics focus. A traversable wormhole needs a controlled violation of that tendency. The exotic source is therefore not decorative material placed around an otherwise complete tunnel. It performs the essential task. Remove it, and the throat normally collapses or develops a horizon. This leads to a straightforward but rather frustrating exchange. General relativity says, here is the geometry of your shortcut. Einstein's equations then add, please provide matter with properties that no known bulk substance possesses. Quantum field theory makes the answer less absolute, but not necessarily more practical. Quantum fields can produce local negative energy densities under certain conditions. The vacuum is not an empty state with every quantity fixed at zero. Its measured energy can depend on boundaries, observers, and the quantum state of the field. The Casimir effect is the best known example. Two closely spaced conducting plates alter the allowed modes of the electromagnetic field between them. Relative to the vacuum outside, the energy density in the gap can be negative. Squeezed quantum states can also produce negative energy intervals. Black hole evaporation involves quantum stress energy effects that can be described using negative energy entering the horizon, while positive Hawking radiation escapes to infinity. These examples show that negative energy is not completely forbidden. They do not show that an arbitrarily large amount can be collected, stored, and spread around a wormhole throat. Quantum field theory appears to restrict both the magnitude and duration of negative energy. A large negative pulse generally cannot last as long as a small one, and negative energy may need to be balanced by positive energy. These restrictions are studied using quantum inequalities. L. H. Ford and Thomas Roman applied such inequalities to static traversable wormholes. Their analysis suggested that a wormhole supported by quantum negative energy would face severe limits. Either its throat would remain close to the Planck scale, or the negative energy would have to be concentrated in an extremely thin region compared with the size of the throat. They concluded that macroscopic traversable wormholes of this type appeared highly improbable. The Planck length is about 1.6 times 10 to the power of minus 35 meters. It is so small that comparing it with an atom is rather generous to the atom. A proton is roughly 20 orders of magnitude larger. A wormhole only a little above the Planck scale would be useless for transporting people, and extremely difficult even for transmitting ordinary signals. Physics at that scale would also require a quantum theory of gravity, so the classical Morris-Thorne description could not be trusted by itself. The alternative is a macroscopic throat with highly separated length scales. The tunnel might have a radius of meters or kilometers, while the exotic layer supporting it could be fantastically thinner. This produces a geometry that is mathematically possible under selected assumptions but looks difficult to construct and sensitive to any disturbance. The quantity of negative energy is not the only concern. Its arrangement matters. The pressure, density, and tension must change with position in exactly the way required by the chosen redshift and shape functions. An engineer cannot simply pour negative energy into a container and place it beside the mouth. The stress energy must be distributed throughout the throat region according to the field equations. A slight error changes the curvature and may create a horizon, a singularity, or a collapsing passage. Morris and Thorne also considered what a human traveller would experience. Traversability means more than drawing a continuous world line from one side to the other. The journey must occur within a reasonable amount of time, and the local acceleration and tidal forces must remain survivable. Proper acceleration is what an accelerometer carried by the traveller measures. A freely falling traveller has zero proper acceleration even while moving through a strong gravitational field. Someone hovering above a black hole can have a large proper acceleration because engines or a supporting structure must continually prevent free fall. A well-designed wormhole could allow the traveller to follow a near geodesic route, reducing the need for continuous thrust. The spacecraft would approach one mouth, pass through the throat, and emerge from the other without experiencing a dramatic local speed. The shortcut comes from geometry rather than from local faster-than-light motion. At every point, the spacecraft remains inside its light cone and travels more slowly than a nearby beam of light. It reaches the distant destination quickly because the route through the wormhole is shorter than the ordinary route through external space. Suppose the two mouths are separated by 1,000 light-years through normal space, while the proper distance through the throat is only a few kilometers. A traveller may cross the internal route in seconds or minutes. A light signal travelling outside would still require 1,000 years. From the viewpoint of the external universe, the journey appears to beat a light beam taking the long route. Locally, no speed limit has been broken. This is similar to two people travelling between opposite sides of a mountain. One follows the road around the mountain, the other uses a short tunnel. The person in the tunnel does not need to move faster. The route is simply shorter. The analogy fails if it is taken too literally because the wormhole connects space-time geometry rather than excavated rock. Still, it captures why general relativity can permit effective faster-than-light travel without allowing local motion through space faster than light. Passenger comfort places limits on the wormhole's curvature. Tidal acceleration occurs when gravity acts differently across the length of the traveller or spacecraft. One side may accelerate more strongly than the other, producing stretching or compression. For a human crossing, the difference between the acceleration at the traveller's head and feet must remain small enough to avoid injury. This generally favours a large throat and gently changing geometry. A very narrow throat can have severe curvature even when it is technically traversable. A beam of light may pass through a route that would crush, stretch, or heat a physical traveller. The lateral tidal force also matters. A traveller moving quickly through curved geometry can experience sideways stresses that grow with velocity. Morris and Thorne included constraints intended to keep both radial and lateral tidal accelerations within roughly Earth-like gravitational limits for a chosen traveller size and crossing speed. The journey time must be considered from two perspectives. The traveller has a proper time measured by a clock on the spacecraft. Observers stationed outside each mouth have their own clocks. A suitable redshift function can keep those times finite and prevent an observer from appearing frozen at a horizon. The mouths can be placed in approximately flat regions, so that ordinary clocks and distances become useful far from the throat. Asymptotic flatness is convenient rather than mandatory for every later wormhole model. It means that the geometry approaches flat space-time far from each mouth. Gravity from the wormhole becomes weak, and observers can define familiar distances and times. A wormhole could instead be embedded in a cosmological space-time, surrounded by matter, or connected to regions with different asymptotic behaviour. Morris and Thorne chose the simpler case because it isolates the properties of the throat. Even the simplest stable model raises the question of how the wormhole was created. Writing down a metric shows that a geometry is compatible with Einstein's equations when supplied with the corresponding stress energy. It does not provide a construction sequence. One possibility is that microscopic wormholes already exist in a quantum gravitational structure at extremely small scales. An advanced civilization might try to enlarge one and prevent it from collapsing. No known method can do this, and the required control over quantum geometry would be far beyond present technology. Another possibility is to change the topology of space deliberately. This faces serious obstacles. Classical general relativity places restrictions on topology change, particularly when causality and ordinary energy conditions are maintained. Singularities or causality violations can appear during an attempted transition. The topological censorship theorem addresses related difficulties. Under assumptions including global hyperbolicity, asymptotic flatness, and the null energy condition, causal observers cannot probe non-trivial spacetime topology. Any usable topological route is effectively hidden or collapses too quickly to be crossed. A traversable wormhole avoids this conclusion only by violating at least one of the theorem's assumptions, most commonly the null energy condition. This reinforces the same message found directly at the throat. ordinary positive energy matter and well-behaved causal structure do not readily permit an observable shortcut. The exotic requirement is connected to broad geometric restrictions, not merely to one equation in the Morris-Thorne model. Stability creates another layer of difficulty. A static solution can be written exactly, but that does not prove it survives perturbations. A traveller entering the throat adds positive energy. Light passing through contributes stress energy. Gravitational waves can disturb the geometry. The exotic supporting material may respond dynamically, moving or changing pressure. If the response amplifies the disturbance, the wormhole may collapse. If it damps the disturbance, the throat may oscillate and settle back to equilibrium. Determining the outcome requires an equation of state for the supporting material and a dynamical analysis of the geometry. The original Morris-Thorne framework treated the wormhole largely as a designed static spacetime. Later work explored stability, rotating versions, evolving throats, different equations of state, modified gravity, scalar fields, electromagnetic fields, and extra dimensions. Some modified theories of gravity move part of the apparent energy condition violation from matter into additional geometric terms. In those models, the material at the throat may satisfy conditions that ordinary matter can obey. While the modified gravitational field provides the effective defocusing, this does not yet establish that such a wormhole exists. A modified theory must agree with experiments, remain mathematically consistent, and produce a stable solution through a plausible physical process. Moving the exotic behavior from the matter side of an equation to the geometry side changes its interpretation, but the unusual effect still has to come from somewhere. Lorentzian wormholes also create a problem that has nothing to do with throat collapse. Once two mouths exist, relativity can shift their clocks relative to one another. Begin with the mouths placed side by side and synchronized. Move one mouth at high speed and bring it back. Special relativity says that less time passes for the moving mouth than for the one that remains still. A similar difference can be produced by keeping one mouth in a stronger gravitational field. General relativity says that its clock runs more slowly relative to a mouth farther from the mass. The internal wormhole connection may preserve a short relationship between the mouths even while their external clocks become offset. Entering one mouth and leaving through the other can then carry a traveller into the external past or future. Morris-Thorne and Ulvi Yurtsever analysed this possibility later in 1988. They argued that if an advanced civilization could create and maintain a traversable wormhole for interstellar travel, it could convert that wormhole into a time machine. The proposal immediately linked wormhole engineering with causality, quantum field theory, cosmic censorship, and the unresolved question of whether negative energy is sufficiently constrained to prevent the construction. The time machine cannot usually take a traveller to a date before the relevant time shift was created. If the mouths were synchronized until a certain operation, the closed causal roots arise only after the offset develops. This would still permit serious paradoxes. A signal could arrive before it was sent. An experimenter might receive instructions from a future version of the laboratory. Information could circulate around a closed loop without a clear point of origin. Stephen Hawking's chronology protection conjecture proposed that the laws of physics may prevent closed time-like curves from forming. Quantum fields near the boundary where time travel becomes possible may grow so strongly that their back reaction destroys the configuration. There is no complete general proof that chronology is always protected. Calculations depend on the space-time and the quantum state, and a full theory of quantum gravity is missing. Wormholes remain one of the main settings in which physicists study the conflict between general relativity's geometric freedom and quantum theory's possible restrictions. These complications make the Morris-Thorne object a dream in two different senses. It is the cleanest mathematical expression of the wormhole people usually imagine. Two accessible mouths, no event horizon, a stable throat, two-way travel, tolerable forces, and a short internal route. It is also a design that depends on physical resources we do not know how to provide. The geometry is clear, the material support is not. No traversable Lorentzian wormhole has been observed. Astronomers have considered whether such objects might imitate black holes, bend light in distinctive ways, or alter the motion of nearby matter. Proposed signals include unusual gravitational lensing, repeated images, light rings, accretion patterns, and gravitational wave echoes. Many of these signatures are not unique. A compact object without an event horizon, an unusual distribution of matter, or imperfections in an astrophysical model can sometimes produce similar effects. Detecting something strange would not immediately justify announcing a wormhole. A convincing identification would require multiple observations that agree with one wormhole geometry and resist more ordinary explanations. At present, the evidence supports black holes, while traversable wormholes remain theoretical possibilities. The Morris-Thorne method remains extremely useful because it turns vague travel requirements into precise geometric conditions. Keep the redshift function finite, select a shape function with a minimum throat, enforce flare-out, calculate the resulting stress energy, check the energy conditions, limit tidal forces, test stability. Every proposed Lorentzian wormhole must answer some version of those questions. Different models change the functions, symmetries, matter fields, or underlying gravitational theory, but the basic examination remains recognizable. The uncomfortable part is the exotic matter. Filling a large region around the throat with negative energy appears difficult and may violate quantum bounds. A natural response is to ask whether the unusual material can be reduced rather than eliminated. Instead of supporting the wormhole throughout a broad volume, perhaps it could be confined to a very narrow surface. The regions on either side could remain ordinary vacuum spacetimes, while all the stress and tension needed to join them would be concentrated at their boundary. Reducing the amount of exotic matter does not solve every problem involved in holding a wormhole open, but it changes the way the problem can be studied. A Morris-Thorne wormhole may require unusual stress and energy throughout a region surrounding its throat. A thin shell wormhole tries to compress that requirement into one narrow surface. The basic construction is often described as cutting and pasting spacetime. This is not a metaphor for hiding an awkward calculation behind craft supplies. The method genuinely begins by taking two mathematical spacetimes, removing selected regions from them, and joining the exposed boundaries. Imagine two identical copies of the exterior of a spherical object. From each copy, remove the central region inside a chosen radius. What remains in each spacetime has an inner spherical boundary. Identify those two boundaries so that every point on one sphere is joined to the corresponding point on the other. The result contains two exterior regions connected at a shared surface. A traveller approaching the boundary from the first exterior does not enter the removed central region. The route continues through the joined surface and outward into the second exterior. That shared surface is the wormhole throat. Nothing has been placed inside the throat because the interior regions were removed before the boundaries were joined. There is no central black hole singularity waiting beyond the entrance. If the cutting radius is chosen outside any event horizon, there is no horizon along the path either. A traveller can move toward the throat, cross the junction, and continue into the other exterior. The geometry is traversable in the causal sense, provided the shell remains open and the crossing does not involve destructive forces. Matt Visser developed simple examples of this construction after the Morris-Thorne work. His approach showed that traversable wormholes could be made by joining otherwise ordinary regions of space-time, while concentrating the energy condition violation at the junction. The exotic matter could be limited to a thin layer rather than spread through a large volume. The procedure can begin with Schwarzschild exteriors. Take two copies of the region outside a chosen spherical radius. That radius must lie beyond the Schwarzschild horizon, associated with the mass. Remove everything inside it from both copies, then attach the remaining surfaces. From either side, the external gravitational field can resemble the field outside a spherical mass. An observer far from the throat may therefore measure a familiar Schwarzschild-like geometry. Closer to the centre, the expected black hole interior is missing. The geometry reaches the shell and continues into another exterior instead. This should not be confused with travelling through a Schwarzschild black hole. The original event horizon region has been excluded from the construction. The mouth is placed outside the radius where a horizon would have formed, and the two remaining pieces are joined directly. The word shell refers to the idealization that all supporting matter is confined to a surface with no thickness. It is similar to treating a soap bubble as a two-dimensional membrane, even though every real soap film has a small but finite thickness. A mathematical thin shell makes the calculation manageable. The spacetime metric can remain smooth on either side, while its derivatives change abruptly at the junction. That change tells physicists what surface energy and pressure must be placed on the shell. The rules used to perform this calculation are called the junction conditions, commonly associated with Georges Damois and Werner Israel. They relate the difference in the way the joining surface is embedded on its two sides to the stress energy contained on that surface. One can think of the surrounding geometry as fabric meeting at a seam. If both pieces naturally lie in the same direction, the seam requires little support. If they pull away from each other, the stitching must provide tension. In a thin shell wormhole, the two exterior spaces flare away from the throat on opposite sides. The junction must hold them in that arrangement. The required surface stress is therefore unusual. For a simple spherical construction made from two identical Schwarzschild exteriors, the energy density on the shell is negative. The pressure can be positive or negative depending on the details, but the null and weak energy conditions are violated at the throat. The exotic requirement has not disappeared. It has been compressed. This is still useful. A broad region filled with unknown material is difficult to describe. A shell can be assigned a surface energy density, a surface pressure, and an equation of state. Physicists can then ask whether the shell remains stable when its radius is disturbed. Suppose the throat begins at a static radius. Give it a small outward push. It may expand briefly and return to its original size. It may continue expanding. It may contract past equilibrium and collapse. The behaviour can be described using an effective potential. The throat radius acts like the position of a particle moving in that potential. A static configuration sits at a point where the effective force vanishes. Stability requires that small movements encounter a restoring tendency, rather than being pushed farther away. Eric Poisson and Matt Visser used linearized perturbations to study this question for spherical thin-shell wormholes. Their analysis links stability to the way the exotic shell's pressure responds when its surface density changes. Some choices produce stable ranges, while others lead to collapse or expansion. An equation of state normally relates pressure, density, temperature, and other properties of matter. For water, gas, plasma, or neutron star material, those relationships can be based on laboratory measurements and established physics. For exotic shell matter, no tested equation of state is available. Researchers can propose mathematical relationships and examine their consequences, but the calculations do not identify a material that can be ordered from a supplier. The shell also has to respond to a traveller. A spacecraft approaching the throat contributes positive energy and gravitational influence. If the supporting structure is delicately balanced, that added energy may disturb the equilibrium. A stable model should survive small perturbations caused by radiation, particles, or the traveller's own mass. Stability against an ideal spherical change does not automatically guarantee stability against uneven disturbances, rotation, electromagnetic fields, or large objects. A perfectly spherical shell can expand and contract uniformly in a calculation. A real disturbance may strike one side first, producing ripples and deformations. The throat might wobble, develop asymmetric modes, or form regions that collapse before the rest of the shell can respond. Thin shell studies therefore examine many backgrounds and many forms of matter. The two sides can be Schwarzschild, Reissner-Nordström, de Sitter, anti-de Sitter, or geometries arising in modified theories of gravity. They can be identical or different. The throat can be spherical, cylindrical, planar, or more complicated. Electric charge can change the stability ranges because electromagnetic effects alter both the exterior geometry and the shell stresses. A cosmological constant can change the large-scale curvature. Rotation can introduce angular motion and make the junction analysis considerably less relaxing. Some modern constructions begin with regular black hole geometries, in which the central singularity has been replaced by a smooth core. Cutting and joining those spacetimes can reduce the amount of energy condition violating matter, and enlarge certain stability regions compared with the simplest Schwarzschild shells. This remains model-dependent rather than a general removal of the exotic matter problem. The attraction of the method lies partly in its efficiency. Most of the spacetime can be vacuum. The strange physics is isolated at a known location, where its properties can be calculated directly. A traveller might cross the throat without spending much time inside the exotic material. In some geometric arrangements, the traveller's path can avoid the material itself, while the exotic stress remains confined to supports around the edge of the opening. Visser's early examples included non-spherical designs intended to minimize direct contact with the energy condition violating region. This does not necessarily make the route harmless. The shell controls the curvature, and the traveller still passes through the geometry it creates. Tidal forces can act even when the exotic substance is not physically touched. The throat size must again be large enough for the intended passenger. A microscopic shell may allow a quantum field to interact with it while remaining useless to a spacecraft. A macroscopic shell requires more extensive support and may be harder to stabilize. A simple thin shell throat has no long interior corridor. The two spherical boundaries are identified directly. Crossing the surface can move the traveller from one exterior to the other, with very little proper distance spent in the junction region. Seen from outside, the mouth may distort light arriving from the opposite side. A ray entering one exterior can pass through the shell and emerge from the other, allowing the throat to act as a gravitational lens and a window. The view would not resemble an ordinary flat pane of glass. Curvature near the mouth can bend rays along multiple paths. An observer might see rings, repeated images, magnified regions, or portions of the far environment arranged in unfamiliar directions. The shell itself might also interact with light if its supporting fields are not transparent. A mathematically thin surface is not automatically optically invisible. The appearance depends on the physical model used to represent the exotic layer. Time can behave differently on the two sides if the exteriors are not identical. One mouth might lie in a stronger gravitational field or connect to a region with a different clock rate. Matching the surfaces requires careful treatment of their time coordinates. If the mouths move relative to one another, the usual time machine problem returns. The cut-and-paste construction makes the throat easy to represent, but it does not prevent relativity from creating a clock difference between the mouths. The shell could then connect events that are separated not only in space but in external time. Closed time-like curves may develop once the time shift becomes large enough. Quantum fields near the boundary where those curves appear may become strongly disturbed. Whether their back reaction always destroys the wormhole is unresolved without a complete quantum theory of gravity. The thin shell places the supporting matter in one location, but causality remains a property of the entire spacetime. There is also a question about thickness. No real material is infinitely thin. Replacing the ideal surface with a finite layer means specifying how density and pressure vary across it. A thick shell may require less extreme values at any single point, but it reintroduces exotic matter throughout a volume. The boundary between a thin shell wormhole and a general Morris-Thorne wormhole becomes less sharp once the material is given realistic width. Quantum effects also resist perfect localization. A field confined to an extremely narrow region has associated momentum and energy uncertainties. If the layer approaches the Planck scale, ordinary quantum field theory on a fixed spacetime may no longer be sufficient. That observation draws the thin shell idea toward microscopic wormholes. A shell can be made smaller in a model, but eventually the geometry itself reaches a scale where it should no longer be treated as a smooth classical background. General relativity describes spacetime as a continuous geometry. A ruler can, in principle, be divided into smaller segments without encountering a built-in smallest mark. Quantum mechanics introduces uncertainty and fluctuations, while general relativity says that energy changes spacetime curvature. Combining those ideas suggests that the geometry should fluctuate at sufficiently small scales. Measuring a tiny distance requires concentrating energy into a tiny region. Concentrated energy gravitates, and too much of it can disrupt the distance being measured. The characteristic scale at which both gravitational and quantum effects become unavoidable is the Planck scale. The Planck length is approximately 1.6 times 10 to the power of minus 35 meters, and the Planck time is approximately 5.4 times 10 to the minus 44 seconds. These values are not simply the smallest distance and shortest duration proven to exist. They are combinations of the gravitational constant, the speed of light, and Planck's constant. They identify a scale where our current theories no longer provide a complete separate description. At ordinary distances, spacetime appears smooth. A table looks continuous, although it is made from atoms. Water looks like a continuous fluid, although it is made from molecules. Spacetime may have its own microscopic structure. The smooth geometry of general relativity could be an average description that emerges only when enormous numbers of quantum gravitational degrees of freedom are considered together. John Archibald Wheeler used the term spacetime foam for the possibility that geometry becomes violently irregular near the Planck scale. Instead of remaining a calm background, it may fluctuate in curvature and topology. Topology concerns the basic connectedness of a space. A sphere and a cube have different shapes, but the same topology because either can be smoothly deformed into the other without cutting or attaching new pieces. A donut has different topology because it contains a hole. If topology fluctuates, tiny handles or connections may appear and disappear. A region that was simply connected could briefly develop a shortcut to another nearby region. That shortcut would be a microscopic wormhole. The word foam should not be interpreted as a literal collection of bubbles floating in an external room. It describes a possible regime where smooth distance, fixed connection, and stable geometry are no longer reliable concepts. A diagram of spacetime foam often shows a surface covered in bumps, loops, and tiny tunnels. The illustration is useful, but there is no established photograph of the Planck scale, and no complete theory confirming that this exact picture is correct. Several approaches to quantum gravity describe microscopic structure differently. String theory begins with extended quantum objects and additional geometric ingredients. Loop quantum gravity describes areas and volumes through discrete quantum states. Causal dynamical triangulations build spacetime from elementary pieces under causal restrictions. Other approaches use spin foams, tensor networks, causal sets, or quantum fields defined around classical backgrounds. Not every approach predicts Wheeler's original foam in the same form. Some suppress topology change. Some allow it only in Euclidean calculations. Some replace microscopic tunnels with patterns of quantum entanglement that reproduce geometric connections at larger scales. The phrase microscopic wormhole therefore covers several different ideas. It may describe a tiny classical-looking throat whose radius is near the Planck length. It may refer to a temporary topology change in a gravitational path integral. It may represent a virtual process rather than a persistent object. It may also refer to a quantum connection that has no single definite geometry until a measurement or semi-classical approximation is chosen. Matt Visser studied a microscopic version of a traversable wormhole using thin shell methods. Two charged spacetimes were surgically joined, leaving the throat radius as the main dynamical variable. That simplified system was then quantized. In the models he analysed, the expectation value of the wormhole radius was of the order of the Planck length. The result made the objects theoretically interesting but unsuitable for interstellar transport. It also suggested that quantum gravity might suppress large topology-changing fluctuations rather than allowing microscopic wormholes to expand freely. A Planck-sized wormhole would be smaller than a proton by roughly 20 orders of magnitude. A proton trying to cross it would be comparable to a large planet trying to enter a tunnel narrower than an atomic nucleus, except the mismatch would be far greater. Even a photon does not behave like a tiny marble that can always be fitted through a small opening. Its wavelength, energy, and interaction with the quantum geometry matter. Sending a very high-energy signal through a Planck-scale throat could add enough energy to alter or destroy the structure. The lifetime may be as restrictive as the size. A virtual wormhole might exist only for a Planck time. Light travels 1 Planck length during approximately that interval. Such a connection would not remain open while a laboratory locates it, aligns equipment, and sends a message. It would appear and disappear as part of the quantum state itself. Calling it virtual does not mean it is secretly an ordinary wormhole that exists for a very brief moment. Virtual objects in quantum theory are elements of a calculation, not directly observable particles following simple hidden trajectories. A virtual wormhole can contribute to an amplitude connecting one configuration with another. The theory sums over possibilities, including geometries with different connections. No single classical tunnel needs to persist between an identifiable entrance and exit. This is one reason microscopic wormholes are difficult to discuss using everyday language. Words such as throat, mouth, radius, and lifetime belong naturally to objects with a definite geometry. A quantum state may contain a superposition of different throat sizes, locations, or even topologies. The wormhole may not have one radius until the relevant observable is specified. It may not connect one definite pair of points. Its geometry may be correlated with the matter and fields around it. An analogy can be made with the position of a quantum particle. A classical ball has one location even when nobody checks it. A quantum state can be spread across multiple possible positions. A quantum wormhole might similarly be spread across geometric possibilities. The classical image of a tunnel would emerge only when fluctuations become small enough for one approximate shape to dominate. Some early quantum gravity proposals imagined a vacuum filled with Planck-sized wormholes. Andrew Strominger described a quantum gravitational vacuum containing Planck-scale wormholes and other non-trivial topological structures in a particular semi-classical model. Stephen Hawking also studied Euclidean wormholes connecting asymptotic regions or connecting two parts of one region. In those calculations, the wormholes could influence low-energy fields and behave as effective interactions from the viewpoint of observers far from the microscopic geometry. These models led to proposals that microscopic wormholes might influence the values of physical constants, the cosmological constant, information loss, or the formation of small disconnected universes. They also produce serious conceptual difficulties. Summing over arbitrary topologies is mathematically hard. Euclidean gravity has problems with convergence. Wormholes can create unexpected correlations between distant experiments, and different approximation methods do not always agree on their interpretation. Observations place indirect limits on some foam models. If space-time fluctuations accumulated strongly while light travelled across billions of light-years, images of distant compact objects could become blurred or their arrival times could be disturbed. Studies using distant quasars and active galactic nuclei have ruled out certain simple random walk models of accumulated space-time fluctuations, while leaving other, weaker models viable. These results constrain particular descriptions of foam rather than proving space-time is perfectly smooth at the Planck scale. Any microscopic effect has to explain why familiar space-time remains so stable. light from distant galaxies forms sharp interference patterns. Atomic clocks agree with extraordinary precision. Particles travel through detectors along paths that can be modelled using smooth geometry. If spacetime is foamy underneath, the fluctuations must average out, cancel, remain extremely small, or affect ordinary matter in ways that current experiments have not yet detected. This is similar to the smooth appearance of air. Molecules move randomly at high speeds, but a person sitting in a quiet room does not feel each molecular collision as a separate storm. The difference is that space-time is not material moving inside another space. It defines the distances, durations, and causal relations used to describe everything else. A fluctuating geometry means the measuring framework itself becomes quantum. Microscopic wormholes are sometimes described as bridges between distant points, but distance is part of the quantity fluctuating. Two locations that appear widely separated in a large-scale geometry may have a small quantum connection, while two nearby labels may not possess a definite separation at the fundamental level. These connections need not permit faster-than-light communication. A temporary topology change can contribute to quantum correlations without supplying a controllable route for signals. Control is the important word. A phenomenon may be present in the quantum state while remaining impossible to select, stabilize, enlarge, or use for communication. Vacuum fluctuations occur naturally, but one cannot ordinarily command a desired fluctuation to appear at a chosen address and remain there until the equipment is ready. A microscopic wormhole that forms unpredictably and vanishes instantly is not a transport system. An advanced technology would need to detect the connection, determine where it leads, prevent it from closing, enlarge its throat, control its energy, and avoid producing a black hole during the process. Enlarging a tiny wormhole requires adding or rearranging energy. Concentrating enough energy in a small region can create strong curvature. The operation intended to open the passage may instead surround it with an event horizon. Negative energy might oppose collapse, but quantum inequalities limit how negative energy can be distributed. The support required for a large throat may be vastly greater than anything available from known quantum effects. A thin shell appears attractive again because it localizes the support. One could imagine a microscopic junction surrounded by negative surface energy, waiting to be expanded. That picture joins two levels of theory that cannot yet be combined reliably. Thin shell equations assume a reasonably definite classical geometry on either side of the shell. At the Planck scale, the geometry may not possess definite sides, a definite radius, or a well-defined surface. The shell itself would need a quantum description. Its radius could fluctuate. Its energy density could be uncertain. It might exist in a superposition of expanding and collapsing states. The surrounding spacetime would also have to be quantized. Treating the throat quantum mechanically while leaving the rest of the geometry perfectly classical is an approximation, useful for exploring possibilities but not a complete theory. The connection between microscopic geometry and quantum entanglement introduces another kind of bridge. Entangled systems possess correlations that cannot be reduced to separate independent states. In some gravitational theories, especially those involving holography, patterns of entanglement are related to spatial connectivity. Reducing entanglement can make a geometric connection narrower, while increasing it can strengthen the connection. This suggests that what appears classically as a wormhole may emerge from quantum relationships. The bridge is not necessarily an extra structure added between two regions. It may be the geometric expression of how their quantum states are linked. The best-known proposal of this kind is summarized as ER equals EPR. It associates Einstein-Rosen bridges with Einstein-Podolsky-Rosen entanglement. The proposal does not turn ordinary entangled particles into portals. It does not allow a message to be sent from one particle to the other faster than light. The associated bridges are generally non-traversable unless an additional interaction changes the system. It does suggest that geometry and entanglement may be less separate than they appear in classical physics. A connected spacetime could emerge because quantum information is organized in the right way. Microscopic bridges would then be more than temporary holes punched through a pre-existing background. They would belong to the process by which the background itself becomes connected. This changes the original foam picture. Instead of imagining a smooth surface covered with tiny random handles, one might imagine a quantum network whose links determine which regions become neighbours when classical geometry emerges. The two descriptions may eventually turn out to be related, or one may replace the other. A complete theory has not settled the question. Thin shell wormholes begin with clear exteriors and add a deliberate seam. Spacetime foam removes the assumption that the exteriors and seam are always definite. Quantum bridges go further by asking whether connection itself is a property of entanglement rather than a separate tunnel. A microscopic bridge becomes more difficult to picture once quantum mechanics is allowed to affect not only the matter passing through spacetime, but spacetime itself. The earlier image of a tiny tunnel appearing in a restless background may still be useful, but it assumes that the tunnel and the background have definite shapes. Quantum theory does not always provide such definite objects. It provides states, probabilities, correlations, and possible outcomes. This is where wormholes begin to overlap with quantum entanglement. Entanglement is one of the most thoroughly tested and least intuitive features of quantum mechanics. Two quantum systems can be prepared in a shared state that cannot be divided into a complete description of the first system and a separate complete description of the second. The systems may be far apart, yet measurements performed on them display correlations that ordinary classical objects cannot reproduce. Imagine preparing two coins in a peculiar quantum state. An ordinary pair of coins can be arranged so that one shows heads and the other shows tails. You may not know which coin shows which result until you look, but each coin can still be assumed to possess its own hidden face. An entangled pair is different. Before measurement, quantum theory does not generally assign each object its own independent result. The shared state describes the pair as a whole. When measurements are compared, their correlations follow rules that cannot be explained by giving each object a fixed set of local instructions. This does not allow someone holding the first particle to control the outcome seen by someone holding the second. Each individual result still appears random. Useful information appears only when the two observers compare their records through an ordinary communication channel. That final step matters. Entanglement cannot be used to send a chosen message faster than light. A person cannot tap one particle 3 times and cause the distant particle to spell out an urgent request for biscuits. The correlations are real, but they are not a controllable signal. The initials EPR come from Albert Einstein, Boris Podolsky, and Nathan Rosen. In 1935, the three physicists published an argument questioning whether quantum mechanics offered a complete description of physical reality. Their reasoning involved two separated systems with strongly correlated properties. Einstein was uncomfortable with the apparent non-local character of quantum theory. He hoped that a deeper description might assign definite properties to each system before measurement. Later experimental tests of Bell inequalities strongly favoured the quantum predictions over broad classes of local hidden variable theories. The EPR paper and the Einstein-Rosen bridge paper appeared in the same year. Nathan Rosen was an author of both, and Einstein was trying to understand two different problems: the completeness of quantum mechanics and the singularities appearing in general relativity. For decades, those problems remained mostly separate. EPR became part of the study of quantum foundations. ER became shorthand for a geometric bridge associated with black holes. The connection between them developed through research on black hole thermodynamics, holography, and quantum information. In 2013, Juan Maldacena and Leonard Susskind proposed the relation usually written as ER equals EPR. ER refers to Einstein-Rosen bridges. EPR refers to quantum entanglement. The proposal suggests that certain entangled systems may be described geometrically as being connected by wormholes. The clearest example involved two maximally entangled black holes joined by a non-traversable Einstein-Rosen bridge. The equal sign is deliberately provocative. It does not mean that every ordinary entangled electron contains a tiny classical tunnel with a measurable diameter. It suggests that space-time connectivity and quantum entanglement may be two descriptions of related underlying physics. One description uses geometry, the other uses quantum information. This idea appears most clearly in holographic theories. The holographic principle proposes that a gravitational system occupying a volume can be described by a quantum theory defined on a lower dimensional boundary. A useful comparison is a hologram, where information recorded on a surface can reconstruct the appearance of a three-dimensional image. The physical proposal is more precise and much more mathematical than an ordinary hologram. The best studied example is the correspondence between gravity and anti-de Sitter space, and a conformal field theory living on its boundary. This is normally shortened to ADS/CFT. Anti-de Sitter space is a space-time with constant negative curvature. It is not an accurate large-scale description of our observed universe, which appears to have a small positive cosmological constant. A DS remains useful because its boundary behavior allows gravitational questions to be translated into quantum problems without gravity. In this correspondence, a black hole in the interior can be represented by a thermal state in the boundary theory. Two related boundary systems can describe a two-sided black hole with two exterior regions. The two boundary theories do not have to exchange ordinary particles. They can remain physically separate while sharing an entangled state. On the gravitational side of the description, that entanglement appears as a connected interior geometry. A standard state used in this discussion is called the thermofield double state. It entangles two copies of the same quantum system, so that each copy, considered alone, looks thermal. The full pair is in a pure quantum state, but either side by itself resembles a system at a definite temperature. The gravitational description is an eternal two-sided black hole, with one exterior corresponding to each copy, and an Einstein-Rosen bridge connecting the interiors. An observer outside the left black hole cannot travel through and emerge from the right side. The bridge remains non-traversable, just like the eternal Schwarzschild connection discussed earlier. Entanglement creates the geometric connection, but it does not make that connection usable. This arrangement helps explain a central point about ER equals EPR. The proposal respects the ordinary rule that entanglement alone cannot transmit information. The associated wormhole is closed to signals. If a message could simply enter one entangled particle and emerge from the other, entanglement would become a faster-than-light communication system. Quantum mechanics does not permit that. The geometric picture matches the information theoretic restriction by supplying a bridge that no signal can cross. The connection may exist without providing a communication channel. That sounds less impressive than a portal, but it is a major theoretical possibility. It suggests that spatial connection itself may emerge from entanglement. Mark van Ramsdonk developed a related argument by examining what happens when entanglement between parts of a holographic quantum system is reduced. In the corresponding gravitational description, the connected regions move farther apart and the geometric bridge narrows. When the entanglement is removed in an idealized limit, the space-time can separate into disconnected pieces. The implication is not merely that entanglement happens inside space-time. Entanglement may help build space-time. A room appears connected because nearby points share a continuous geometry. From the quantum perspective, that continuity might result from a dense pattern of entanglement among more fundamental degrees of freedom. Reducing those connections would not simply empty the room. It could remove the geometric relationship that made the locations part of one room in the first place. This idea has influenced modern approaches using tensor networks. A tensor network is a mathematical arrangement used to represent complicated, entangled quantum states. Its links record how different parts of the state are connected. Certain networks produce structures resembling spatial geometries. The number and pattern of links can determine approximate distances and areas in the emergent space. These networks are simplified models rather than complete maps of our universe. They demonstrate how geometric ideas can arise from quantum information without assuming that space exists independently at the start. ER equals EPR takes that relationship into the black hole interior. Two strongly entangled black holes may be connected because the entanglement is the quantum description of the bridge. This proposal was partly motivated by the black hole firewall problem. According to ordinary general relativity, a sufficiently large black hole should have a smooth event horizon. A freely falling observer should cross without encountering a physical wall at that exact location. Quantum theory says that Hawking radiation emitted by an old black hole must be entangled in a way that preserves information if black hole evaporation is unitary. Difficulties arise when one also demands the usual entanglement across a smooth horizon. A single quantum system cannot be fully entangled with two independent systems at once. This restriction is called the monogamy of entanglement. The firewall argument suggested that one of the expected relationships must fail. Perhaps the horizon is not smooth. An infalling observer could encounter high-energy radiation instead of an uneventful crossing. Maldacena and Susskind proposed that the relevant entanglement might be organized through wormhole connections. ER equals EPR was not presented as a complete final solution to every black hole information problem, but it offered a new way to think about the interior. Instead of treating entanglement between a black hole and distant radiation as an unexplained link across an otherwise ordinary spacetime, the entanglement might be part of the spacetime's quantum connectivity. The bridges involved would be extremely complicated. Hawking radiation contains many quantum degrees of freedom distributed across a vast region. Its entanglement with the remaining black hole would not resemble one neat tube connecting two spherical mouths. The corresponding geometry, when such a description exists, may be highly quantum and impossible to represent as one smooth classical tunnel. ER equals EPR therefore does not give us a collection of tiny pipes attached to every entangled particle. It proposes deeper equivalence between quantum correlations and geometric connection. In simple, highly organized states, the geometry may be smooth enough to recognize as an Einstein-Rosen bridge. In general states, the connection may have no ordinary classical shape. The proposal is also a conjecture, not an experimentally established universal law. It is well motivated in holographic settings, especially for black holes and strongly entangled systems with known gravitational dual descriptions. Whether the same interpretation applies literally to every entangled pair remains unclear. An electron in a laboratory and a photon on the other side of the building do not come with a confirmed semi-classical gravitational geometry. Their combined mass is far too small for a classical bridge to appear in the usual sense. Any ER connection associated with such a pair would be quantum, non-traversable, and not directly represented by Einstein's classical equations. This protects causality while making the claim difficult to test. A bridge that cannot transmit signals and has no measurable classical geometry is not something a telescope can photograph. Researchers instead test the mathematical consequences in theories where both descriptions are available. A calculation can be performed using the entangled boundary theory and compared with a calculation performed using the gravitational wormhole. When both give the same result, confidence in the relationship grows. A major development arrived when Pingao, Daniel Jaffrus and Aaron Wall found a controlled way to make a holographic Einstein-Rosen bridge traversable. They considered an eternal black hole in anti-de Sitter space, with two entangled boundary systems. Under ordinary conditions, the bridge is non-traversable. They then introduced a carefully timed interaction coupling the two boundaries. That interaction changes the quantum stress energy in the bulk. It produces negative average null energy along the horizon. The resulting gravitational back reaction shifts the geometry enough for a signal to pass from one side to the other. The operation does not open a tunnel by pushing its walls apart mechanically. It alters the quantum fields and therefore alters the causal paths available through the bridge. Before the coupling, a signal entering the left side cannot reach the right exterior. After the negative energy effect, a narrow window opens in which the signal can emerge. The wormhole is traversable, but only under carefully controlled theoretical conditions. This might appear to permit faster-than-light travel. The external boundary interaction prevents a causality violation. The two sides must be coupled directly. That coupling itself represents a channel between them. The protocol cannot transmit information outside the causal limits already allowed by the complete setup. The wormhole route and the boundary description are two ways of describing the same process. In the boundary theory, information is transferred using entanglement, an interaction, and quantum dynamics. In the gravitational description, a signal passes through a temporally traversable bridge. This is where wormhole travel and quantum teleportation become closely related. Ordinary quantum teleportation transfers an unknown quantum state from one system to another. The protocol begins with entanglement shared between the sender and receiver. The sender performs a joint operation involving the state to be transmitted and their half of the entangled pair. Classical information about the result is then sent to the receiver, who performs a corresponding correction. The original quantum state is destroyed during the process. It is not copied. This respects the no-cloning theorem. The receiver reconstructs the state only after the classical information arrives. Teleportation therefore does not send usable information faster than light. In the holographic wormhole protocol, the coupling between the two sides plays a role related to the classical communication and interaction required for teleportation. The information entered on one side becomes recoverable on the other. From one viewpoint, the state has been teleported through a strongly entangled many-body system. From the dual gravitational viewpoint, it has travelled through a traversable wormhole. The two descriptions are not competing stories about where the information really went. Under holographic duality, they describe the same process using different variables. One description contains quantum operations and entanglement. The other contains geometry, negative energy, and a path through a bridge. This is why some physicists describe traversable holographic wormholes as geometric teleportation. It is also why the process does not produce a hidden faster-than-light channel. Quantum teleportation already requires communication. The wormhole version remains consistent with that requirement. The amount of information that can pass is limited. Sending a signal adds positive energy to the wormhole. Too much positive energy counteracts the negative energy opening and can close the route. A single small message may cross while a large stream cannot. The bridge is less like a permanently open motorway and more like a carefully timed access gate that notices the weight of every vehicle. The signal also affects the geometry through back reaction. In quantum gravity, information is not a harmless label floating across an unchanged background. Encoding and transmitting information requires physical degrees of freedom, and those degrees of freedom carry energy. Later models made traversability last longer. Juan Maldacena and Xiaoliang Qi constructed an internal traversable wormhole in a nearly two-dimensional anti-de Sitter gravitational theory. Their system used two coupled quantum models known as Sachdev-Yekitaev, or SYK systems. The coupling generated negative null energy and supported a traversable geometry. Unlike the brief opening in the original Gauss-Jafrus wall protocol, the connection could remain traversable while the coupling was maintained. The SYK model contains many interacting fermionic degrees of freedom with random couplings. It is not a complete model of ordinary matter, but it has useful properties connected with quantum chaos, black holes, and holography. At low energies and with many degrees of freedom, its behaviour can be related to a simple theory of gravity in nearly anti-de Sitter space. Two suitably coupled SYK systems therefore provide a setting where a many-body quantum problem has a gravitational interpretation resembling a traversable wormhole. Again, this does not mean two boxes of ordinary laboratory particles create a literal tunnel in the space between them. The wormhole belongs to the dual gravitational description of the quantum system. The model teaches physicists how entanglement, interaction, negative energy, and geometry fit together. It does not provide an engineering diagram for a portal between cities. Four-dimensional theoretical examples have also been constructed. One model uses charged massless fermions to generate a negative Casimir-like energy that holds open a long wormhole between near-extremal magnetically charged black holes. The solution is highly specialized and depends on fields and conditions far removed from an ordinary astronomical environment. Such work is important because it shows that traversable quantum wormholes are not limited to one simplified two-dimensional equation. It also shows how demanding the construction remains. The black holes must have carefully chosen charges. The quantum fields must provide the required negative energy. The system must avoid instability and causality violations. The surrounding geometry must satisfy the assumptions of the model. Nature has not supplied observational evidence for such an arrangement. Quantum computers introduced another way to examine these ideas. A programmable quantum processor can imitate the mathematical evolution of a small quantum system. It does not need to reproduce every physical ingredient directly. A computer simulating a hurricane does not become wet, and a quantum processor simulating a wormhole does not acquire a gravitational tunnel behind the cooling equipment. In 2022, a team led by Daniel Jaffris and Maria Spiropoulou reported an experiment using a quantum processor to simulate dynamics related to a traversable holographic wormhole. They implemented a small model inspired by SYK physics, prepared two entangled quantum systems, inserted quantum information on one side, applied a coupling, and recovered the information from the other. The observed process was interpreted through the connection between many-body teleportation and traversable wormhole dynamics. The experiment did not create a wormhole in physical spacetime. No opening appeared in the laboratory. No matter entered the processor and emerged elsewhere. The device carried out quantum operations whose mathematical description was intended to reproduce selected features of a model with a wormhole dual. The distinction was sometimes lost in headlines. Wormhole created in a quantum computer sounds more dramatic than small entangled system implemented to investigate a proposed holographic correspondence, although the second description is considerably closer to what happened. The interpretation later became the subject of a technical dispute. Critics argue that the simplified Hamiltonian used in the processor did not thermalize as expected, and that some apparent gravitational features resulted from its small, commuting structure rather than robust wormhole behavior. They concluded that the model lacked important properties required for a convincing gravitational interpretation. The original team responded that the criticism examined behavior outside the implemented protocol and maintained that the observed teleportation mechanism and dynamics remained consistent with the intended gravitational interpretation during the relevant time interval. The disagreement does not concern whether a physical space-time tunnel appeared. Both sides are discussing whether the small quantum model adequately reproduced the specific dynamics expected from a holographic wormhole description. This is a normal difficulty in quantum simulation. A small system may imitate selected features of a larger theory without reproducing all of its behavior. A model aircraft in a wind tunnel can reveal useful aerodynamic effects without carrying passengers across an ocean. Problems begin only when the limitations of the model are ignored. Quantum processors may eventually simulate larger systems with stronger evidence of scrambling, thermalization, and holographic behavior. Such experiments could test calculations that are too difficult for ordinary computers. They would still be simulations unless the quantum system itself had a well-established gravitational dual. Even then, the word wormhole would refer to the dual description, not necessarily to a tunnel curving the laboratory's physical spacetime. This distinction does not reduce the scientific value. Quantum gravity is difficult to test because Planck scale effects are tiny under ordinary conditions. Holographic duality offers the possibility of studying gravitational questions through accessible quantum systems. A processor may reveal how information spreads, how entanglement changes, and how a teleportation protocol corresponds to motion through an emergent geometry. The experiment is closer to testing a dictionary between two theories than constructing the object described by one side of that dictionary. ER equals EPR remains attractive because it connects several problems that once appeared unrelated. It links the smoothness of black hole horizons with entanglement. It relates the growth of spatial geometry to quantum information. It turns certain teleportation protocols into descriptions of travel through a wormhole. It suggests that distance and connectedness may not be basic ingredients of nature. The proposal also remains limited. It is best understood in theories with holographic duals. Our observed universe is not known to be described by the simplest anti-de Sitter models. Ordinary entangled particles do not produce measurable classical bridges. No experiment has shown that two astrophysical black holes become connected by creating entanglement between them. Preparing black holes in a controlled, maximally entangled state is not a task waiting for a larger laboratory budget. Even when an ER bridge is present in a theoretical description, it is normally non-traversable. Making it traversable requires an added interaction and a carefully generated negative energy effect. Entanglement alone provides correlation, not transport. This point prevents a common misunderstanding. Suppose two particles are entangled and one is carried to Mars. Measuring the first particle on Earth does not open a route to Mars. It does not send a signal through a microscopic bridge. The observer on Mars sees random results until ordinary information arrives from Earth. ER equals EPR does not change the predictions of quantum mechanics. It offers a possible gravitational interpretation of the correlations. The bridge is not an extra channel added to the theory. It is another way of describing relationships already present in the entangled state. A similar warning applies to quantum teleportation. The word teleportation suggests that matter disappears and reappears elsewhere. Actual quantum teleportation transfers the state of a system, not the material object carrying it. The original carrier remains at the sending location and loses the state being transmitted. A separate system at the destination acquires that state after the protocol is completed. Teleporting the full quantum state of a human would require controlling an unimaginable number of degrees of freedom, transmitting the necessary classical information, and reconstructing the state in another physical system. Nothing in the Wormhole protocol avoids those difficulties. A holographic signal passing through a dual wormhole can be described more directly as travelling along a bulk path, but the boundary description still obeys quantum communication rules. The equal sign in ER equals EPR therefore hides a careful relationship. It is not an instruction to replace every entanglement diagram with a drawing of a tunnel. The geometry becomes clear only for particular states, usually involving many strongly interacting degrees of freedom. The wormhole may be smooth when the entanglement has the right organized structure. Change the state, and the interior can become longer, shorter, more complicated, or no longer well described by classical geometry. The length of an Einstein-Rosen bridge can grow with time even while the exterior black hole appears unchanged. This has led to connections between interior volume, quantum complexity, and the difficulty of preparing the corresponding boundary state. Quantum complexity measures how many simple operations are required to build a state from a chosen reference state. A highly complex entangled state may correspond to a long wormhole interior. The throat need not become narrow in the same way a physical pipe narrows. The internal distance grows because the emergent geometry reflects increasingly complicated quantum relationships. These ideas are still being developed, and different proposals relate complexity to different geometric quantities. They show how far the wormhole concept has moved from its original role as a bridge between two classical sheets of space. A quantum wormhole can represent entanglement, information flow, computational complexity, or a term in a gravitational path integral. Not all of these structures are the same object. A non-traversable ER bridge connects entangled black holes without carrying messages. A gauge-aferous wall wormhole becomes briefly traversable after a boundary interaction creates negative average null energy. A Maldacena key wormhole remains open in a specially coupled low-dimensional model. A microscopic foam wormhole may be a fluctuating topology with no definite classical shape. Using one name for all of them is convenient. but the differences determine what each object can do. None provides an uncontrolled shortcut that violates causality. The non-traversable bridges carry no signal. The traversable holographic models require interactions that already respect the causal structure of the full system. Quantum teleportation requires classical communication. The theory repeatedly allows the appearance of a shortcut while keeping careful account of how information moves. This may be the most important result of quantum wormhole research so far. Gravity and quantum mechanics do not merely place independent restrictions on a tunnel. They may describe the tunnel and the entanglement as parts of the same structure. A bridge that looks geometric from one viewpoint can look like a communication protocol from another. Negative energy in the gravitational description can correspond to a precisely chosen interaction in the quantum description. The traveller and the teleported state are not necessarily two separate stories. They may be dual accounts of one event. There remains a major gap between those controlled models and the universe outside the equations. The known constructions rely on anti-de Sitter boundaries, large numbers of degrees of freedom, special interactions, near-extremal black holes, or simplified gravitational theories. Our universe does not provide an obvious pair of boundary laboratories where a double trace coupling can be switched on. Astrophysical black holes are surrounded by accretion flows, magnetic fields, radiation, and disturbances. Creating the required entangled state would be difficult. Maintaining it while controlling the mouths would be more difficult. Producing the correct negative energy without destabilizing the geometry would add another difficulty, in case the first two seemed lonely. Quantum wormholes are therefore not close to becoming transportation devices. Their value lies in what they reveal about the possible foundations of space. They suggest that separation may be a feature of the quantum state, rather than an absolute starting condition. Two systems can be far apart in the emergent geometry, while remaining parts of one inseparable quantum description. A wormhole makes that inseparability visible in geometric language. The remaining question is how such quantum connections enter calculations when ordinary Lorentzian time is no longer used. The gravitational path integral changes the role of a wormhole before it changes the shape. In ordinary Lorentzian space-time, one direction is time, light cones determine which events can influence one another, and a traveller follows a future-directed path while a clock measures the journey. In a Euclidean calculation, the time coordinate is transformed so that it behaves more like an additional spatial direction. The result is not the space-time experienced by an observer. It is a mathematical geometry used to calculate quantum amplitudes. The transformation is commonly called a Wick rotation. In a simple flat space-time calculation, ordinary time, written as t, is replaced by a new coordinate related to imaginary time. The word imaginary refers to the imaginary number used in the transformation. It does not mean that the calculation is invented or meaningless. This change can turn rapidly oscillating quantum expressions into exponentially weighted ones that are easier to analyze. Instead of adding phases from many possible histories, the Euclidean path integral assigns weights connected with an object called the Euclidean action. The method is widely used in quantum field theory because it converts some difficult problems into forms resembling statistical mechanics. Temperature, imaginary time, partition functions, and quantum amplitudes become closely related. Gravity makes the procedure less secure. In quantum field theory on a fixed background, the stage remains in place while the fields fluctuate. In quantum gravity, the geometry of the stage must also be included in the sum. One tries to add contributions from many possible geometries, perhaps including different shapes and topologies. A smooth Euclidean wormhole can appear as one of those possibilities. There are no ordinary light cones in a fully Euclidean geometry. No direction is selected as the future, and a person cannot move through the structure while aging in the familiar way. Asking how long a traveller spends inside a purely Euclidean wormhole is therefore like asking how long someone spends walking across a map that contains no time coordinate. The wormhole can still connect two regions. Its geometry may have two wide ends joined by a narrow throat. but the connection represents a contribution to a quantum calculation rather than an available transport route. This distinction is essential because Euclidean wormholes are often drawn using the same funnel-shaped pictures used for traversable Lorentzian wormholes. The drawings look similar while answering different questions. A Lorentzian wormhole asks whether a signal can enter one mouth and emerge from another. A Euclidean wormhole asks whether a connected geometry contributes to an amplitude, a partition function, or a proposed quantum state of the universe. The objects most strongly associated with early Euclidean wormhole research are the Giddings-Strominger wormholes. Stephen Giddings and Andrew Strominger studied gravity coupled to an axion field, represented in their calculation through an antisymmetric tensor field strength. They found smooth Euclidean solutions containing a throat supported by axion flux. Their instantons could describe the nucleation of small baby universes. An axion is a type of scalar field with a shift symmetry. Axion-like fields appear in particle physics and string theory, although the field in a particular wormhole model is not automatically the same particle sought in dark matter experiments. The axion charge passing through the Euclidean throat helps prevent the geometry from closing at a singular point. Spheres surrounding the centre shrink toward a minimum radius and then expand on the other side. In a simple presentation, the wormhole resembles two large Euclidean regions connected by a handle. One end can be associated with a parent universe, while the other can lead to another large region, or to a baby universe that branches away. A baby universe does not have to be small for its entire existence. The name refers to the way it appears as a new connected component in the topology-changing process. After separating, its internal geometry could expand while its entrance remains microscopic or disappears from the parent region. An outside observer might never be able to enter the baby universe or retrieve a signal from it. Its effect would instead appear indirectly through the quantum amplitude assigned to the process. The Giddings-Strominger solution was often described as an instanton. An instanton is a Euclidean solution that contributes to a non-perturbative quantum process. It is similar in role to a tunneling path in quantum mechanics. A particle in ordinary quantum mechanics can cross a barrier even when classical physics does not provide enough energy for the crossing. The Euclidean version of the particle's motion helps calculate the probability. A gravitational instanton applies a related method to fields and geometry. The process may involve a change that has no ordinary classical Lorentzian path, such as the nucleation of a universe or a change in topology. The Euclidean solution does not necessarily describe every stage as a literal event. It provides a saddle point around which the path integral can be approximated. A saddle point is a configuration for which small variations do not change the action at first order. In an ordinary integral, one can approximate the answer by finding points where the exponent changes slowly. Quantum gravity attempts something similar in a vastly more complicated space of geometries. This semi-classical approximation assumes that a recognizable smooth geometry gives the dominant contribution in the region being studied. Quantum fluctuations are then considered around it. That is already a strong assumption. If the curvature is close to the Planck scale, uncontrolled corrections may become important. If many topologies contribute with comparable weight, one saddle cannot tell the whole story. The original axion wormholes could have throats near the Planck scale, although later models have examined larger and more controlled solutions in supergravity and string theory settings. Explicit higher dimensional embeddings have shown that some Euclidean axion wormholes can be placed in 10-dimensional supergravity regimes, where curvatures and couplings are parametrically controlled. Those constructions also reveal unresolved puzzles when compared with the expected properties of their holographic boundary theories. A controlled classical solution is not the same as a confirmed contribution to the complete quantum theory. The path integral contour must be chosen, fluctuations must be examined, and negative modes can alter the interpretation. A negative mode is a direction in the space of fluctuations along which the Euclidean action decreases rather than increases. Its presence can indicate that this saddle describes an instability or a decay process rather than a stable correction to the vacuum. Studies of the Giddings-Strominger solution have disagreed over the relevant negative modes and over the correct treatment of the Euclidean contour. Some analyses interpreted the contribution as imaginary, which would suggest instability against baby universe production, rather than an ordinary real correction to low-energy physics. This is one reason Euclidean wormholes remain controversial. The geometry can be written clearly while its proper role in quantum gravity remains uncertain. Stephen Hawking examined wormholes that connect two asymptotically Euclidean regions, or two parts of the same region. In his treatment, closed universes could branch off from a larger parent spacetime. Their unobservable states would affect the description available to an observer who remained in the parent universe. If information enters a baby universe and never returns, the parent observer may have to average over possibilities that cannot be distinguished locally. This can make an initially pure quantum state appear mixed. A pure state contains the maximum quantum information allowed by the theory. A mixed state represents uncertainty over several possible states. The difference matters because ordinary quantum evolution is expected to be unitary. Unitary evolution preserves the full information encoded in a quantum state. Baby universes appear to provide a route by which information could leave the observable region. This raised concerns similar to the black hole information problem, although the geometry and calculation were different. Sidney Coleman proposed another interpretation. Instead of producing observable loss of quantum coherence, repeated microscopic wormholes could act like effective interactions in the parent universe. A small wormhole has two ends. From the low-energy viewpoint, one end might appear at one event and the other at another event. The detailed throat would be too small to resolve. Integrating out the microscopic connection could add a non-local interaction between the two events. Coleman argued that these effects could be rewritten using quantities known as alpha parameters. For observers in one large universe, the alpha parameters would behave like fixed but initially unknown coupling constants. Different large universes could inherit different values. A process that looked random because of invisible baby universes could then become ordinary quantum evolution with particular constants once the relevant alpha state was selected. Coleman applied this framework to the cosmological constant and argued that Euclidean wormholes could produce a probability distribution strongly favouring a vanishing value. This proposal attracted considerable attention, because the observed cosmological constant is extremely small compared with simple quantum field estimates, although it is not exactly zero. The argument relied on several approximations and soon encountered objections. William Unruh argued that the same wormhole effects could produce a highly non-local Euclidean action that was unbounded below, undermining the quantum theory rather than selecting a desirable constant. Other concerns involved large wormholes, interactions among wormholes, the correct measure in the path integral, negative modes, and the question of whether the semi-classical expansion could be trusted after the wormhole contributions were summed. The proposal did not become the accepted solution to the cosmological constant problem. It remains historically important because it showed how tiny changes in topology might affect quantities measured at much larger scales. Euclidean wormholes return to the centre of quantum gravity research through holography. The new problem was not mainly the cosmological constant, it was factorization. Suppose a quantum theory contains two completely independent systems. The combined partition function should be the product of the partition functions of each system. A measurement performed in the first system should not become mysteriously correlated with a disconnected second system unless the two are prepared with a shared state or interaction. In a gravitational path integral with two separated boundaries, a disconnected geometry gives the expected product. A Euclidean wormhole connecting the two boundaries produces an additional connected contribution. That contribution correlates the boundaries. The gravitational answer no longer factorizes in the simple way expected from two fixed, independent quantum theories. This is called the factorization problem. It is especially sharp in ADS/CFT, where gravity in the interior is supposed to be equivalent to a definite quantum theory on the boundary. If the boundary consists of two independent conformal field theories, their partition functions should factorize. A connected Euclidean bulk wormhole appears to say otherwise. One possible interpretation is that the gravitational path integral does not describe one definite boundary theory. It may describe an average over an ensemble of theories. In an ensemble, quantities that factorize in each individual member need not factorize after averaging. Fluctuations in the underlying couplings can create correlations between the average partition functions. This interpretation works naturally in some low-dimensional gravitational models, including Jakob-Title-Bohm gravity. There, connections with random matrix ensembles provide a precise explanation for certain wormhole contributions. It remains unclear whether the same ensemble interpretation should apply to every gravitational theory, particularly a theory intended to describe one definite universe, rather than an average over possible theories. Euclidean wormholes may therefore be revealing missing information about how the path integral is defined. They may need to be included with additional sectors, cancelled by other contributions, or interpreted through hidden degrees of freedom such as baby universe states. The issue is not that the equations contain a visibly incorrect tunnel. The issue is that a smooth connected geometry seems to calculate correlations that the presumed boundary theory does not possess. Replica wormholes provided a case where connected Euclidean geometries produced an extremely useful result. To calculate quantum entropy, physicists often use the replica trick. Instead of calculating the entropy directly, one studies several copies, or replicas, of the system, joins them according to a prescribed pattern, calculates a quantity for an integer number of copies, and then analytically continues the result. In a gravitational calculation, the geometry must also be summed over. One possible saddle keeps the replicas separate. Another saddle joins them through wormholes. These are replica wormholes. They connect different copies used in the entropy calculation. They do not connect separate universes that a traveller can visit. Including them changes the entropy of Hawking radiation from an evaporating black hole. Hawking's original semi-classical calculation suggests that the entropy keeps rising as radiation accumulates. Unitary evolution requires a different behaviour. The entropy should rise initially, reach a maximum around the page time, and then decrease as information becomes recoverable from the radiation. The resulting curve is called the page curve. In 2019, independent analyses showed that replica wormhole saddles produce the decreasing part of the page curve in controlled gravitational models. As the black hole ages, a connected replica geometry becomes more important than the disconnected one. The calculation leads to the island rule, in which part of the black hole interior is included when determining the entropy of the radiation. The word island refers to a region that is not physically located inside the external radiation collector, but is included in its entanglement wedge. Information in the island can be encoded in the radiation. Replica wormholes therefore help explain how the gravitational calculation avoids the endlessly increasing entropy predicted by the simplest Hawking treatment. They do not show a particle escaping through a hidden pipe. They alter the calculation of which degrees of freedom belong to which quantum subsystem. This result gave Euclidean wormholes a more secure role in certain semi-classical entropy calculations. It also strengthened the link between topology, quantum information, and black hole interiors. Questions remain about the most fundamental interpretation. The replica method first works with an integer number of copies, but the entropy requires continuation toward one copy. The connected geometry used during the calculation is not necessarily a Lorentzian object present inside one ordinary spacetime. Its contribution may be best understood as part of the mathematical machinery required to calculate entropy. Turning it into a literal tunnel would add claims not supported by the method. Euclidean wormholes can also be continued into Lorentzian cosmologies in selected models. One can cut a Euclidean solution along a suitable surface and analytically continue one coordinate so that it becomes time. The resulting Lorentzian region may describe an expanding universe. A complete Euclidean wormhole can sometimes be divided into two halves, with each half providing initial conditions for a Lorentzian cosmology. Recent models have used asymptotically anti-de Sitter Euclidean wormholes to define wave functions that continue into inflating universes. These are proposals within quantum cosmology and holography, not observations of our universe's origin. The continuation must be chosen carefully. Not every Euclidean solution has a real, smooth Lorentzian interpretation. Fields that are real in Euclidean signature may become complex after continuation, and the appropriate contour can depend on the boundary conditions. Even when the continuation works, the Euclidean throat is not necessarily preserved as a traversable Lorentzian passage. It may become a moment of minimum size, a cosmological bounce, a pair of expanding regions, or a tunneling configuration. The word wormhole survives because of the Euclidean topology, not because passengers can cross it. Euclidean calculations also change the meaning of distance between the ends. Two asymptotic boundaries can be connected through the bulk geometry while remaining independent locations in the Lorentzian interpretation. The wormhole can contribute to a correlation function without providing a causal signal. This mirrors the distinction encountered with ER equals EPR, although the mathematical frameworks are not identical. A connected calculation does not automatically create communication. The unresolved questions are substantial. Does the gravitational path integral include every topology? Which integration contour is correct? Are the known wormhole saddles stable? Do they describe one theory, an ensemble, or sectors labelled by baby universe states? Can a higher dimensional ultraviolet completion preserve the solution without violating consistency conditions? No single answer has been accepted across all models. Euclidean wormholes are useful precisely because they expose those questions in a concrete geometric form. They have contributed to studies of axions, symmetry-breaking, baby universes, the cosmological constant, holographic factorization, black hole entropy, and quantum cosmology. They have not provided a route for an astronaut. Returning to travel requires restoring Lorentzian time, light cones, causal paths, and physical mouths. But there are questions about whether a connected geometry contributes to a probability, to whether an observer can enter one region and emerge in another, where the mouths are, how their clocks compare, whether they can be reached, and what happens when ordinary matter tries to pass between them. Restoring ordinary time turns the two ends of a wormhole into physical locations with clocks, histories, and surroundings. The local geometry near a throat may look similar in several models, but the global destination depends on how those ends are embedded in the larger spacetime. The simplest traversable arrangement places both mouths in the same universe. One might be near Earth, while the other lies near a distant star. Outside the wormhole, the two locations are separated by the ordinary interstellar distance. Through the throat, the proper distance can be much shorter. An inter-universe wormhole connects different asymptotic regions. Each end opens into a region that extends outward as its own large space. The two regions belong to one complete mathematical spacetime, but they cannot be reached from each other through the ordinary exterior. The eternal Schwarzschild, Eisner-Nordstrom, and Kerr extensions already supplied versions of this structure. Their extra exteriors were blocked by horizons, collapsing bridges, singularities, or unstable Cauchy horizons. A traversable inter-universe wormhole would remove those obstacles. An observer could enter through one asymptotic region and emerge into another without crossing a one-way event horizon. The second region need not have different laws of physics. It could be another exterior governed by the same fields and constants. Calling it another universe describes its global separation from the first, not necessarily a new set of particles or a purple sky. More speculative models connect a parent universe to a baby universe. The baby region may branch off through an early quantum process and develop its own expanding interior. From the parent side, the entrance could resemble a black hole or a microscopic throat. From inside the baby universe, the geometry could appear large, because internal volume is not determined only by the size of an external opening. A small neck can lead to a region with considerable spatial volume. An ordinary bag provides a limited analogy. Its opening can be narrower than the space inside. Spacetime geometry permits a much greater difference, because curvature determines the relationship between area, distance, and volume. The baby universe may eventually disconnect. If the throat pinches off, there is no remaining route between the parent and child regions. Such a process is sometimes described as universe creation, rather than a permanent wormhole. A temporary connection participates in the birth, but no traveller can use it afterward. Other models keep a connection open through exotic fields or modified gravity. The two regions then remain parts of one connected Lorentzian spacetime. No observation has shown that our universe is connected to another asymptotic region, or that astrophysical black holes contain baby universes. These possibilities arise in exact solutions, semi-classical tunneling models, and proposed theories of quantum gravity. The absence of observation is partly caused by the object's own causal structure. A baby universe hidden beyond a horizon may have little or no ability to influence the exterior after formation. A traversable mouth would be less discrete. It could transmit light, matter, and gravitational influence. The far side might alter lensing, orbital motion, radiation, and the mouth's response to disturbances. This raises a difficult question about conservation laws. If an object enters one mouth and leaves another universe, has energy disappeared from the first region? In the full connected space-time, the energy has not simply vanished. It has moved through the throat. Observers who consider only one exterior may see an apparent loss, just as energy passing beyond an event horizon is no longer available locally. The global accounting depends on the symmetries and boundary conditions of the complete geometry. Defining total energy can be subtle when a spacetime has several asymptotic regions. An artificially controlled wormhole would require clear rules for momentum. A spacecraft entering one mouth carries linear and angular momentum. The mouths or their supporting fields must react so that the full system satisfies conservation laws. If the mouths are oriented differently, a traveller can emerge moving in a direction that appears unrelated to the original approach. The wormhole structure and its supports must absorb the corresponding change. The mouths are not passive holes cut in empty space. They are gravitating parts of a physical system. Their histories become especially important when the clocks at the two ends stop agreeing. Begin with two mouths positioned beside one another. Assume that the internal path is short and that clocks placed beside the mouths are synchronized. Now move one mouth at a speed close to the speed of light. After a journey, return it near the stationary mouth. Special relativity says that less proper time passes along the moving mouth's path. This is the same effect used in the twin paradox. The mouth that travelled may have aged by 1 year while 10 years passed for the mouth that remained behind. Their external clocks now differ by 9 years. If the wormhole's internal geometry continues to connect corresponding moments along the two mouth histories, stepping through can bridge that difference. A traveller entering the younger mouth could emerge beside the older mouth at an earlier or later external time, depending on the direction of passage and the way the mouths were moved. A gravitational time shift can produce the same result. Place one mouth near a massive object while keeping the other far away. Gravitational time dilation makes the lower mouth's clock advance more slowly. After the mouths are reunited or positioned conveniently, the wormhole retains the clock offset created by their different histories. Morris, Thorne and Ulvi Yurtsever showed that a traversable wormhole permitted for interstellar travel could be converted into a time machine using these relativistic effects. Their argument did not require a new type of exotic tunnel. Once a stable traversable wormhole exists, ordinary time dilation can create the dangerous arrangement. This does not usually allow travel to a time before the wormhole or its time shift existed. If the mouths were synchronized until 2050 and the offset was created afterward, there is no established route through the device to 1920. The earliest reachable time is limited by the histories of the mouths and the formation of the causal loop. That is disappointing for anyone planning to warn a historical figure, but it still creates a major problem. A signal could return to a point after the wormhole was built but before the signal was sent. Suppose the mouths are 1 light hour apart through external space, but the clock difference between them is 2 hours. A traveller enters the younger mouth and leaves the older one 2 hours earlier. The traveller then moves through ordinary space for 1 hour to reach the first mouth. Arrival occurs 1 hour before the original departure. A closed time-like curve has been formed. The traveller's path always remains locally slower than light, but the combined route through the wormhole and external space returns to an earlier event. This is the crucial feature of a wormhole time machine. No one locally overtakes a nearby light ray. The causality violation comes from the global arrangement of space-time. The result creates familiar paradoxes. A traveller might prevent the journey that produced the traveller's arrival. A message could instruct its sender not to send it. Information might circulate around the loop without ever being created by an ordinary process. A physicist could receive a complete set of equations from a future visitor, publish them, and later send the same equations into the past. The equations would exist, but no one would have derived them. This is called a bootstrap or information origin paradox. It does not produce a direct logical contradiction, but it weakens the usual relationship between causes, explanation, and creation. One possible response is self-consistency. Only histories that fit together without contradiction would occur. A traveller could attempt to prevent the original departure, but would fail through some chain of events. The failure need not involve a mysterious force. The traveller's actions may simply turn out to be part of the history that already led to departure. Friedman, Morris, Novikov, Thorne, Yurtsever, and their collaborators studied classical field evolution in spacetimes containing closed time-like curves. They found examples in which self-consistent solutions can exist, although the usual initial value formulation becomes more complicated and questions of uniqueness remain. Self-consistency prevents contradiction by restricting the allowed histories. It does not explain why nature should permit closed causal loops in the first place. Quantum mechanics offers several proposed responses. A process could be restricted to self-consistent quantum states. The traveller could emerge into another branch of a many-worlds description. Interactions around the loop could produce probabilities that avoid contradiction. No interpretation has been experimentally selected because no closed time-like curve has been observed. The more immediate possibility is that the wormhole fails before the loop forms. The boundary at which closed time-like curves first appear is called a chronology horizon. Before that boundary, the space-time still has an ordinary causal region. Beyond it, some future-directed paths return to their own past. Light rays can circulate around an almost closed path near the chronology horizon. Each circuit can blue-shift the radiation, or make repeated contributions accumulate. The energy of quantum fields may grow large. That energy curves space-time and can alter the wormhole. Stephen Hawking formulated the chronology protection conjecture, proposing that the laws of physics prevent the formation of closed time-like curves. He argued that quantum stress energy could become very large as causal paths approach closure, producing back reaction that disrupts the configuration before a time machine appears. This has been compared with feedback from a microphone placed too close to a loudspeaker. A small signal circles the system repeatedly, grows, and overwhelms the intended operation. A wormhole chronology horizon is far more complicated, but the repeated path idea captures part of the instability. Calculations in selected geometries support this possibility. Vacuum polarization, or particle production can grow near the chronology horizon, and gravitational back reaction can become important before the loop is completed. The result is not a universal proof. The renormalized stress energy depends on the quantum field, the state, and the global geometry. Some calculations produce divergences, while others encounter ambiguities near the point where semi-classical gravity itself becomes unreliable. A complete answer probably requires quantum gravity. Hawking's conjecture remains a compelling expectation rather than an established theorem covering every possible time machine. The uncertainty leaves three broad possibilities. Traversable wormholes may be impossible. They may exist but become unstable when a clock offset approaches a causal loop. They may permit time shifts while quantum mechanics enforces self-consistency by a mechanism not yet understood. All three remain theoretical because the starting object has never been observed. A wormhole inherited from the early universe might avoid the need for a civilization to create new topology. The universe's first moments involved far greater densities, temperatures, and curvature than any modern laboratory can produce. Quantum gravitational fluctuations could have created microscopic connections. Inflation might then have stretched some structures to larger scales. This idea is attractive because inflation expands distances enormously. A tiny object present before or during rapid expansion could become macroscopic afterward. Expansion alone does not guarantee survival. The throat-supporting fields must also evolve correctly. A wormhole can be stretched while its energy density dilutes, its tension changes, or its geometry becomes unstable. The two mouths may be driven apart faster than local signals can control them. The throat could collapse, form horizons, or become diluted into a configuration that no longer functions as a shortcut. Cosmological wormhole models attempt to embed a throat inside an expanding Friedman, Lemaitre, Robertson, Walker background. The surrounding universe grows while the wormhole radius follows its own dynamics. Some solutions use exotic matter in ordinary general relativity. Others rely on scalar fields or modified theories of gravity. The existence of an exact solution does not prove that the early universe naturally produced the required initial conditions. Phase transitions offer another formation mechanism. As the early universe cooled, fields may have selected different vacuum states in different regions. Boundaries between them are called domain walls. Closed domain walls can contract under their tension. Depending on their size, vacuum energy difference, and gravitational field, the collapse may form a primordial black hole or a wormhole leading to a baby universe. A 2024 analysis of domain wall networks found theoretical conditions under which delayed wall collapse can produce primordial black holes and wormholes connected to baby universes. The result is a model-dependent production mechanism, not evidence that such objects formed in our universe. Cosmic strings, monopoles, vacuum bubbles, and other topological defects have also appeared in speculative wormhole scenarios. Their intense fields can curve spacetime in unusual ways. A primordial wormhole would need to survive billions of years. It would encounter radiation, matter, gravitational waves, and cosmic expansion. A microscopic throat might evaporate or collapse through quantum effects. A macroscopic one might accumulate matter that changes its geometry. A mouth acting as a gravitational lens could attract material and become surrounded by an accretion flow. If the object is traversable, matter could pass through rather than collecting behind a horizon. Its observational appearance might differ from a black hole, but modelling the difference requires assumptions about the far-side environment. A bright star near the second mouth could illuminate the first from within. Gas could flow through the throat. Magnetic fields might connect the two regions. No accepted astronomical observation requires this explanation. Primordial wormholes remain possible objects in selected theories rather than a known cosmic population. Extra spatial dimensions create another collection of possibilities. General relativity normally describes 3 dimensions of space and 1 of time. higher dimensional theories add one or more spatial directions that may be compact, warped, or inaccessible to ordinary matter. A sheet of paper provides a familiar analogy. 2 points far apart along the sheet can be close through the three-dimensional room around it. Creatures confined to the sheet would see the direct path as a shortcut through an additional dimension. A higher dimensional wormhole could operate in a related way. Our observable universe might be a three-dimensional brain embedded in a higher dimensional bulk. Standard model particles could remain confined to the brain while gravity propagates through the bulk. A bulk path might connect two brain locations more efficiently than a route restricted to the brain. From our viewpoint, the signal would appear to take a shortcut. Such scenarios are called brain-world models. The details determine whether a shortcut is causal, traversable, and consistent with observations. Juan Maldatzina and Alexei Milakhin identified humanly traversable wormhole solutions in a Randall-Sundrum brain-world setting. The extra-dimensional model supplies effects unavailable in the standard model and can produce a large wormhole with tolerable travel time and tidal forces under highly specialized assumptions. The result does not mean known particle physics predicts a buildable wormhole. Randall-Sundrum models introduce a warped extra dimension, brains, and a relationship between gravitational scales that remains hypothetical. The construction also relies on black holes with particular charges and on quantum fields that provide the necessary negative energy. Its parameters must satisfy both theoretical and experimental restrictions. It demonstrates that the phrase humanly traversable is not automatically inconsistent with every mathematical theory beyond the standard model. It does not demonstrate that nature selected that theory or produced the object. String theory offers additional ingredients. Strings, higher dimensional brains, fluxes, compact dimensions, and scalar fields can support geometries that do not exist in four-dimensional vacuum general relativity. Some solutions resemble Lorentzian wormholes, others are Euclidean saddles, black hole throats, or non-traversable holographic bridges. Extra dimensions can move the exotic behavior into fields produced during compactification. From a four-dimensional viewpoint, those fields may appear to violate an energy condition even when the complete higher dimensional theory has a different interpretation. This does not remove the need for consistency. The compact dimensions must remain stable. Ghost fields must be avoided. Quantum corrections must remain controlled. The solution must fit with known limits on deviations from gravity's inverse square law. Experiments have tested gravity at distances far below a millimeter and have not found a confirmed extra-dimensional deviation. Collider searches and astrophysical observations also constrain many models. Large or strongly coupled extra dimensions therefore cannot be added freely whenever a wormhole calculation needs assistance. Artificial wormholes face the most direct version of every problem. A civilization would first need a seed. Creating a wormhole from completely ordinary spacetime may require topology change, and classical results suggest that topology change can produce singularities, causal problems, or violations of energy conditions. A microscopic quantum wormhole could provide the seed without requiring a new handle to be formed classically. The civilization would then have to find it. A Planck scale throat is around 10 to the power of minus 35 meters across and may survive for roughly a Planck time. Detecting one among quantum fluctuations would require access to a regime where ordinary notions of position and duration are already uncertain. After detection, the throat would have to be stabilized. Negative energy, or an equivalent modified gravity effect, would need to prevent immediate collapse. The throat would then have to be enlarged. Adding ordinary positive energy tends to increase gravitational focusing, which works against the desired flare-out. A procedure that concentrates too much energy may form an event horizon around the seed. The attempt to manufacture a passage could create a black hole instead. Casimir systems produce measured negative energy relative to the surrounding vacuum, but the magnitude is tiny and the geometry is restrictive. Two conducting plates do not provide a container of negative material that can be poured around a throat. Quantum inequalities limit the duration and magnitude of negative energy distributions available to quantum fields. Models claiming to use arbitrarily small total negative energy can still require extreme curvature scales, submicroscopic layers, or travel times that make the throat effectively unreachable. Assume those problems are overcome and a macroscopic throat is created. The mouths must then be separated. Moving one mouth requires accelerating the supporting geometry, and whatever fields maintain it. A mouth large enough for a spacecraft may have an enormous effective mass or energy content. The acceleration can produce radiation and stress. The two mouths must remain internally connected while their external positions change. If the mouth is electrically or magnetically supported, moving it through surrounding plasma creates additional interactions. If it is tied to a black hole, the black hole's mass and charge must be controlled. The destination creates another difficulty. A newly created wormhole does not automatically place its second mouth near a desired star. If both mouths begin in a laboratory, one mouth must be carried to the destination through ordinary space. The first expedition receives no shortcut. Once the mouth arrives, later journeys can use the wormhole. Construction would resemble building a railway whose first section must still be transported by road. A primordial or quantum connection might already link distant places, but its destination would need to be discovered before use. Sending a probe through could reveal the far side if the probe survives and signals can return. The exit might lie inside a star, between galaxies, near a black hole, or in a universe with no accessible matter. Random topology is not obligated to respect holiday plans. Targeting a destination would require controlling the global connection itself. No known theory explains how to choose a distant point and attach a new mouth there without first interacting with that region through ordinary causal means. The finished wormhole must tolerate traffic. A spacecraft adds positive energy, momentum, heat, electromagnetic fields, and quantum fluctuations. Its gravity changes the throat. If the stability margin is small, the passage may collapse around the vehicle. A reliable design must remain stable under repeated use, uneven loading, radiation from both ends, and accidental impacts. The two environments can have different pressures and temperatures. Gas may rush through the throat from the denser side. Radiation can cross continuously. A mouth placed near a star and another in interstellar space could become a powerful energy channel. The resulting flow would alter the supporting fields and possibly destroy the geometry. Tidal forces must remain tolerable. The throat cannot contain regions of curvature that stretch the vehicle beyond its structural limits. Acceleration through the mouth must also remain manageable. An apparently short distance does not guarantee a smooth journey. A tunnel through a mountain can be short and still contain a very sharp turn. Wormhole geometry can be short and still impose violent tidal changes. Clock management would be essential. Any relative motion or gravitational difference between the mouths creates time dilation. A transport company interested only in distance might accidentally construct a time machine after moving one terminal or parking it near a massive planet. Preventing closed time-like curves could require continually adjusting the mouth positions and clock rates. The permitted configurations might become severely restricted. Quantum chronology protection could disrupt the throat before the dangerous offset is reached. That would make the device safer for causality and less useful for transportation. Artificial construction must therefore solve geometry, quantum field theory, materials, stability, navigation, conservation laws, and causality at once. The energy requirement is not known because no accepted construction procedure exists. Popular estimates sometimes compare the task with stellar or galactic energies, but the answer depends completely on the model. A large throat with gentle curvature might require enormous distributed negative energy. A higher dimensional design might shift the requirement into brain tension or compactification scales. A holographic wormhole might use an interaction between two entangled systems rather than a macroscopic shell, but known examples do not provide a portal in our laboratory spacetime. The most responsible engineering estimate is therefore not a very large number. It is that the required technology and even the required physical ingredients are unknown. A search for existing wormholes may be more realistic than construction, although it remains extremely difficult. A mouth can bend light differently from a black hole. Light may pass through and return from another environment, rather than disappearing behind a horizon. The lensing pattern can include unusual rings, repeated images, brightness changes, and apparent motion that does not match an ordinary compact mass. Matter orbiting the mouth could respond to gravity from both sides. A star near the far mouth might influence motion near the first through the connected geometry. Gravitational waves striking one mouth may produce signals involving the throat's internal modes. A merger between a compact object and a wormhole could differ from a black hole merger. Many proposed signatures are shared by other exotic compact objects. Accretion physics is uncertain, and weak signals can be confused with ordinary environmental effects. A convincing detection would require several independent measurements agreeing with one geometry. The object would need to lack an ordinary event horizon, exhibit the expected lensing or wave behavior, and resist explanations involving a black hole, neutron star, or modeling error. Until then, primordial, higher dimensional, inter-universe, time-shifted and artificial wormholes remain different solutions to different theoretical problems. Some connect separate asymptotic regions. Some create baby universes. Some become time machines after their mouths age at different rates. Some use extra dimensions to reduce the burden on four-dimensional matter. Some begin as microscopic fluctuations and depend on an imagined technology to enlarge them. The labels can overlap. A primordial wormhole could be higher dimensional. An artificial wormhole could connect two universes. A traversable inter-universe bridge could become time-shifted. What separates the models is not the word attached to them, but the answers to practical questions. Does the geometry have ordinary Lorentzian time? Are both mouths accessible? What supports the throat? Can matter cross? Does the root contain a horizon? Are the two ends in the same asymptotic region? Do their clocks agree? Can the configuration form without a singularity? Does it survive quantum back reaction? Those questions leave the exotic possibilities organised rather than merely strange, and they also indicate what an observation would need to establish before a distant compact object could reasonably be called a wormhole. And so, we return from the strange edges of space-time, having crossed bridges that collapse, tunnels held open by exotic energy, quantum connections, and possible doors to other universes. No wormhole has yet been observed, but each one helps physicists test what gravity, causality, and reality may allow. If this journey helped you relax, please leave a like, subscribe, and share where you are listening from tonight. For now, let the equations fade, let the distant stars remain distant, and allow your thoughts to slow. Sleep well, fellow traveller, and may every path ahead feel gentle, quiet, clear, and kind.